Okay, good morning everyone. So we're happy to invite you back to our Senior Project Symposium. We are happy also to have, I'm trying to think of your name right now.
Oh, Ryan Trent.
Ryan Trenham, yes. Ryan Trenham, who was previously from MCW Miracore and is now working with NBCC, has been for the past, what, 2-3 years, Ryan?
2 years.
2 years, yes. And so Ryan's been out in the industry, knows what the industry is about, and is now here working with us at NBCC, and we're happy to have him here today. We also are glad to have Dhruvraj Patel here to present his wireless tank level indicator. Go ahead.
Thank you, Mr. Brock. Good morning to all presented attendees in person and watching me through virtual. My name is Dhruvraj Patel, and I am an electronics engineering technology student in the industrial stream at NBCC Moncton campus. Today I will be presenting my SPL Symposium as a wireless water tank level indicator. This project has been totally advised under the advisor named Mr. Shilal, and also there are so many. All of the instructors were very helpful throughout this project. Before going in the depth of my presentation, I would like to share a basic overview what I will be discussing in my whole presentation. So, what is the purpose of this device? So, if any technical or a non-technical user is coming through first time coming across this first time to this device or a product, so where it is applicable, what is the purpose of this use, and what are the limitations of this product. Also, as my title of my project suggests, it is a wireless, so it has a transmitter unit and the receiver unit for wireless communication. And also, I would like to share my PCB designing experience, which was my first. This was my first PCB designing in my electronics engineering career. So I would like to share my advantages, what I have learned, and also what issue I have faced during the PCB designing, and also how I fix that, how it works. And also one of the most important thing I would like to also discuss the time taken throughout this project and the cost. It is under budget or over budget. I will be concluding in my conclusion with my feedback. So as we go through the in a wireless communication, the transmitter unit is also and the receiver transmitter unit and the receiver unit are working at the same position. So the transmitter unit in my project is consist of encoder. I have considered as a heart of my transmitter unit. And as for the sensor, I am using the concept of transistor as a switch for sensing the level of the water from the tank. And for the different variation of the water tank, I have used my potentiometer to adjust and vary according to the size of the water tank. Before it was I was placing just a resistor of 10K, but in my EDR it was advised me to have it is better to have a potentiometer, so I have changed it to another version. So in a receiver unit, so it consists of decoder. So especially what's the encoder mean, I would like to share. The encoder is a thing like it takes a message and it encodes that message into the information such as in a binary 0 and 1, and it will transmit through a RF module, and if the transmission is valid, then the decoder will consider that input as an input, and it will display whether if you are using a LED display out. Here I'm using LED as a display output, or it can be also used as a LCD as a display output. So this is a basic overview of my project. It's a concept drawing. So I haven't mentioned the dimension. I haven't got a particular time to fix my concept drawing. But the size of the encoder and the enclosure and the receiver unit enclosure is the same. Is in a length of 4.3 inches by width of 3.28 inches, and it's a height of half of inch of height, 1.5 of inch of height. So as you can see this 5-volt line, this is a 5-volt line, the first one, which is connected at the end of the water tank, and the levels are set as per the size of tank, like the low, medium, full, and the overflow. So in a various concept, especially this concept is mostly the wireless water tank concept is mostly used in Asian country, especially in India, where I'm coming from. So we used to have a separate personal water tank at the top of our house for each and every house. So we used to take water from the main source line from the municipal. So we used to know what's the level of the water, what's the level of the water in a tank. So it is mostly used in our country. So I use this concept. And the receiver unit is will display what's the level of the water is in a tank, and also it will display if the transmission is getting valid, if any range issue is there, or if someone has changed the channel of the dip switch, it will freeze the level of the LED, and it will not consider as a valid transmission. So this is my transmitter block diagram. So for the block diagram, for the transmitter, I am feeding a 9-volt in my input volt power source input. So I can give from the 9-volt word adapter, or also I can use a 9-volt battery. For the demonstration purpose, I have used a 9-volt battery. There is a voltage regulator which converts from 9-volt to 5-volt, and if the voltage conversion is perfect, then it enables the power LED, and and also the 5-volt goes to the encoder IC HT12E, which is my encoder IC. So once this IC is powered, and it will the water level sensor, as I said before, I'm using the concept of transistor as a switch. So it will start switching. If any switch goes from high to low, or it change any like on or off, it will transmit that data to the receiver side. Transmit that data into encoder, and also the 8-way channel select is one of the most important thing in this project. So there is in this encoder IC, it has 8 address bit and 4 data pins, 4 data bits. So total, the encoder can encode the data of a 12 bit. And there is a resistive oscillator for this for oscillating the network. And if the 8-way channel select will transmit zero, if the once the user has set their channel or 0 or 1, and it will transmit into encoder, and all this encoder will gather the data and start and release as a data output in a, as this data output I am considering as a transmitter module. So the data output is a transmitter module over here in a block diagram. And I have make a note over here. So I am using a RF module for wireless communication. It's a 433 megahertz RF module. And for the receiver side, first thing is the same. I'm using a battery for input power source, and voltage regulator is a 7805 for converting 9 volt to 5 volt. So once the IC for the decoder, the IC name is HT12D, and once the decoder is powered, so it will verify first the data input is valid or not, and also the address bit, the 8 address bit, it should be same as the encoder have. Like user need to set both the channel as same. If they have the different channel, then it will not consider as a valid transmission. So if the channel select matches with the encoder, and it will display the valid the LED will be displayed as a valid transmission output. And also over here it is have a resistive oscillator network. And also I have to test I also have a test point to measure if anything, if the circuit is having a perfect 5 volt in on the path. And I have as a LED display output for displaying my level of the water. So this is my transmitter unit schematic. So I am filling the 9 volt as a barrel there, and this C1 is a C1 and C2 decoupling capacitor. So for C1 for C1 it gives a fit bypass path, and C2 acts as a transient response time. It will manage that. And the concept of transistor as a switch. So once the circuit is powered, and for my screw terminal, I have the fifth one as my 5 volt supply, which I have told before. It will connect it at the end of the water tank, and the 4, 3, 2, 1 are just my level. I have adjusted according to the level: low, medium, full, and overflow. So once the voltage is coming through this line, firstly the transistor will be in a cutoff region. So there is a no current, like IC and IE. The base current and the collector current will be 0, and it will be having the voltage for V, C, and E. VCE will be having a maximum like a 5 volt, which I am feeding. So once the transistor will be in a saturation mode, it will send the data to the AD, the series of AD from AD8 to AD11, which are the following connection according to the level. And as I said before, it has a 8 address bit from A0 to A7, which is connected to the dip switches for as a channel select. And the 4 data pins are AD8, AD9, AD10, and AD11, which are the data bits for that. And I have a resistive oscillator for 1.1 megaohm. So for the 1.1 megaohm I have taken from the data sheet of the XT12E. They have the graph on choosing the particular register for oscillator network. And for the transmitter, the transmitter work based on the as a technique of amplitude shift keying. So as the carrier wave will be work as an amplitude modulation when once the data signal is updated. So as the data signal is updated, it will generate a particular the shift key. So so I have this connection for my transmitter unit. So as I said before, this is a graph for choosing correct resistance for oscillator. So I have a 5 volt over here for my voltage input. So it goes with the 1.0 to 1.1 mega ohm. So datasheet recommend me to use a 1.1 mega ohm for oscillator network. And the frequency oscillator is a 3 kilohertz for my this transmitter unit. So as I have told that these sensors are based on transistor as a switch. So this is the closed loop of my sensors. This schematic is a receiver unit of my is a receiver unit of schematic. So I have the receiver is a four pin. Is of a 4 pin. So one is for the NBCC, and 2 and 3 are the data which are data input which are connected together, and the fourth pin is a ground. So once the data is received from the transmitter module, it will from the transmitter side, it will go in with data in, and it will verify the first series of the address bit. If the address bit are matching with the encoder, the transmitter unit, then only it will consider, then only it will display this data pins as a output. So I have connected this as my outputs are low, medium, full, and overflow for my as my display output. So I have there is also a valid transmitter. So the valid transmission will be actively low for a while, but once if it receive any transmission from a RF, valid transmission from a RF module transmitter unit, so it will display from blinking for a second. So here it's the same concept of C3 and C4 are the decoupling capacitor and power LED. I have to check if the circuit is working or not, and I also have a test point for testing whether I'm getting a 5 volt in my circuit or not. So as for this resistive oscillator for the receiver unit, I have chosen a 51 kilo ohm for the decoder side. So as I am feeding a 5 volt to my receiver unit, so it goes with the 51K over here. Yeah, 51K is over here. So 51K I'm giving to my I'm using as a receiver resistive oscillator resistive oscillator, and I'm getting a 150 kilohertz as in my frequency oscillator for the receiver unit. So this is my first PCB design in my electronics engineering career. So I have revised various revision for this, and this PCB is totally designed based on the guidance which was given from the CSR, and because I haven't known, I was unknown about the rules, what how the pads, what the pad size should be, how the path should be considered. So it was a totally new experience for me, and I haven't used before any KiCad in my life before. So I learned this software, like how on designing the schematic and also the PCB. So it was quite interesting and challenging for me for on designing the PCB. This is a back copper view of my PCB design. So the main issue I faced after the designing was when I was drilling these pads. So some of the pads are in a minimum size of 12 mil. So when I was drilling with a 0.7 drill machine, it took my whole this path from, and like the drill machine didn't came out as proper as it should be, and it took my like 3 of this part. So it makes my circuit like not in working condition. So the thing I did is I disconnected some of the part which got a short circuited. So I just connected with the jumpers, solder with the jumpers, and as a manually we are connecting. For a jumper I'm using a zero resistance jumper, which was recommended to use, not a wire jumper. So yeah, and on the main thing of on this PCB designing, Mr. Leisure showed the process how to design a PCB in a photo, over here in our NBCC college. What's the process they are following? So it was quite interesting for me to know how the process follows on designing PCB. So the time was given for like 4 months to make this product. I started from the December of 3rd. I gone to with this project idea to Mr. Shilal, and he was quite interested in my project. So he was my advisor, I just finally completed this product in a working condition by 22nd of May 2022. Yeah, this project, the main thing of this project was RF module. Mr. Silla was very helpful in that. The tuning process is very difficult because this RF module are quite cheap and inexpensive, so they are very hard to get tuned. So definitely we need an oscilloscope, and it takes like 1 hour, 2 hours to get a proper tune. So yeah, the RF module was more challenging in this project. Sometimes it comes in a working condition, and after, like, if you check after an hour, it will not work. So yeah, it was quite fun. So in a conclusion, I finally made this product in a working condition as it was expected, as it was expected and the required criteria. And the the cost which I have assigned was $150, but I use only $113 before the government taxes, so, and the shipping charge. So if I include that, it would be around about $140. So my estimate was almost perfect on this project. So yeah, the main drawback of this device is because of my RF module, I am having a range issue. I'm not having a good range for communication purpose. But this can be solved by this can be solved by using a good quality of RF module. So yes, I'm facing this range issue still. So yeah, this was my project presentation for with the product I have built in my last 4 months. So, yeah, I will demonstrate my product. So for the demonstration, I'm not using a top cover for of the enclosure. The reason behind was as I said, RF module are are in a good range. So if I cover my RF module, it stops working. So I have talked with and make arrangement with my with my advisor, and he agreed on this demonstration without having a top lead. So yeah, this is my receiver unit, and this is my transmitter unit, which I am using as my transmitter unit. This is the receiver unit. So before presenting, my deep switch channel are same at this moment for valid transmission. So now I have some amount of water in this bucket, so it's showing at a low level. So if I increase you can see this yellow LED is for the valid transmission. If anything comes from the transmitter unit, it will blink for a while. If yeah, so now it's gone to the medium level of my tank. So I have to do this type of thing. So this is my full level, and this is my overflow. So I have an issue with the medium level at some time, but it stays stable. Yeah. So this was with the same address bit on the transmitter unit and the receiver unit. But if I change a pattern of first I will outside of this, and I'm changing this pattern. I'm changing, and I'm not changing the pattern at the transmitter unit. So once I will power this, it will not display what it will display what it was running before. So yeah, it will not consider as a, if I do anything with the water tank, it will not. But once I will do what the transmission should be had, yeah, so it goes in what the state is should be for the water tank. So this was my demonstration for my project.
Is there a power switch on the unit?
No, I was using a wall adapter, but the thing was I ordered from the Amazon, and they gave me the wrong product, like negative sleeve on the top and the positive. So I was not able to use.
It looked like it was an illusion, but it looked like you pushed on the circuit board and that turned it on and off. So I was just wondering how you powered it off and back on.
No, I just unplugged the barrel jet.
Oh, we couldn't see that part because it was down below. Okay, I was just wondering. I was like, that's magic. He's got a touch-sensitive PCB.
I was just
good.
Barrel jet. Yeah, so this was my project, what I was building in from last.
Yeah.
Yeah.
Okay, good. Anybody want to start with questions?
Well, since you have this up on the board, that LED next to the power, what was that called, the V?
Value transmission.
Yeah, how does
The
that
yellow.
function exactly?
So at the, see, if the transmitter doesn't send any data to the receiver, it will stay off in at that condition. Once the data is sent by the transmitter, it will check if the transmission, if the IC will check if the data which is being sent by the transmitter is correct or not, and then after it will display as a valid transmission.
Okay, so the light indicates a valid transmission?
Yeah.
When you switched the channel earlier, it was on, so to me that would say that it's having a valid transmission, but it wasn't transmitting at all, was it?
Just a second.
It stays on if you change the channel, right? So it's indicating it's a
Yeah.
valid transmission, but in fact it's not, right?
Good observation.
Yeah. So
You could
that
incorporate something.
should be a proper like a tuning.
Yeah.
So this receiver is require a proper tuning. Like I have changed like 3 of receiver with Mr. Siddhar, and we
Okay.
try to tune it. So there will be issue with the tuning problem. But yeah, when we were testing, it was staying off at that point.
Okay, I was just curious. Thanks.
Yeah, while we're here, you had mentioned that you had a problem with the mid-level indicator.
Yeah.
Can you explain, do you understand what the issue is? Have you investigated that? And can you explain what's going on there?
Yeah, the before, like when I tested as a function during the functionality test, so if all the level are detected, so the medium level was not coming, not blinking with the when all levels are detected. But yesterday I just fixed that one. So when the now, yeah, so now it's working. Before it was not. So that might, I changed the battery because it might be a battery issue. So when, yeah, now it's like all the LEDs are working. Before the yellow LED was not working when all the cell is overflow.
Can you bring us back down through so it's not overflowing, but it's at your maximum level? Can you bring us back down to medium? Can you just pull the electrodes up? Or adjust your level that way, yeah? It's always nice to see it work the other way too, right? Yeah. We don't want it just to record the level
One
once
way.
and then it doesn't do anything after that, right? Yeah.
See, this is the medium level.
Medium, yeah. So you're at medium, so can you make it go to low?
Low.
Yeah, okay. And if it goes empty, then?
Remove all the,
There, if it goes empty, then all the indicators are off?
Indicators are off.
Okay. And is it, by the design, it's only supposed to transmit when it sees a change? Is that what's supposed to
Yeah.
happen? So right now, nothing's changing, but it's transmitting all the time? Is that?
Yeah, so I don't know why now it's like this LED, but before it was, no.
That's interesting, yeah. So that was,
See, now
it's the transmitter unit that, are they both powered, are they both plugged in, or is one on a,
no, both are plugged
they're
in.
both plugged in, okay.
So now see this, So due to this transmitter, so if I go like anything object is near to my receiver,
Okay.
it will detect as a data, but it will not display to my LED output.
Okay. Any other questions?
Yeah, that should be the case. It should be off.
Should be, yeah. It should only be transmitting with a C to
Yeah.
change.
Yeah.
Yeah.
Bring up the schematic or something.
Yeah, yeah.
And look at the drawing.
Yeah, if there's no other
Yeah.
questions on this, then we could go to the schematic, yeah?
I'm all right.
No, that's okay.
I'm good.
Yeah, okay, yeah. So bring up your schematic, please.
This is for the transmitter unit.
Okay, so we could start with C1 and C2. I think in your presentation, you referred to them as decoupling capacitors. Would you maybe re-explain what C1 and C2 are there for? Why are those needed? What could happen if either the value of C1 or C2, we'll talk about each, I'll get you to talk about each one. If the value is not selected correctly, based on the data sheet recommendations, or if C1 and C2 are not present, you know, those kinds of things. Maybe that's too many questions at once, but can you explain again what C1 and C2 are there
For
for?
the C1 is considered as a CE. So what I understood from the data sheet and what I got, so it's for the stability, and the filter. I used to put as a filter over there for noise issue.
Is it a filter?
No, it's not a filter because I don't have a resistor over there.
Right,
So
so it's,
I was considering it for the stability,
so stability, okay.
and for the C2, I was considering as a transient risk, like the distance from the output, like a 5 volt, and IC is around like 1 inches from my board.
So let's just stay on C1 for a minute. So when you say stability, like with respect to what? Like what are we talking about here?
Just to
What can happen if C1 is not present?
like this, so it will be like sometimes the more voltage can affect the.
And it's especially if there are long leads on the input of the regulator.
Sorry.
It's especially true if there are long leads on the input of the regulator. The stability part is especially true and especially required if there are long leads or long traces, right,
Yeah.
on your circuit board, say, leading to the regulator. Okay?
Yeah. So.
And why did you choose 10 microfarads?
Yeah, I use a 10 micro 50 because to limit, so if any, before I connected the wall adapter, I was unknown to that the negative was on a top and the positive is inside on my sleeve. So when I plugged in, it came, the voltage regulator became very hot in a few seconds. So, and at that time my capacitor was, the C1 was damaged. So I'm not sure.
So did you change the value after that happened? Or did you?
No, I just replaced the.
Okay, I'm just curious because 10 microfarads is not the value recommended by the manufacturer. So I was just wondering.
From the data sheet, I just realized because I have used this value in my breadboard prototype, but after that I have gone through the data sheet of 7805. They are using a 0.3 and 0.33 micro.
Yeah, 0.33, yeah.
And a 0.1 micro for.
Right, you're right. So why, I'm just wondering why, you know, do you have a set of calculations that showed, that justified using a 10 microfarad instead of the manufacturer recommended value? I'm just wondering.
I don't have an actual calculation for using.
So
10.
so that's the nature of my question. So how did you come about this 10 microfarad value when the manufacturer is recommending 0.33? That's my question.
So I use I thought like in any of the circuit we are mostly using 10 micro 25. So
Do you think that just because you're using 10 microfarads in other places in the circuit, that means it's a valid choice to put a 10 microfarad here?
not actual. It will not work for everything.
So you just sort of
Just
accidentally placed a 10
Yeah.
microfarad capacitor there?
Yeah, so I just tested that as a 10 micro. At that time, what I have, I just put it and I just got 5 volt.
Okay, so you
So-
installed it and it worked.
worked.
You didn't have any problems, so you
No.
just thought, well, I'll stick with that.
Yeah.
Okay, so it wasn't really an engineering approach here. Okay. All right, so what about C2? Is C2 the value that was recommended by the manufacturer? What was the recommended value there?
It's a 0.1 micro.
0.1, right? So this was the same, so this was an economics kind of choice, was it? It's like you had a whole bunch of 10 microfarad capacitors and you didn't want to spend the money on. Okay, it obviously works though, right? Okay, so that's good. I just thought that was worth kind of asking those questions. I see you have a question too.
Yeah, just, I'm wondering, like, where you have TP1 cycles, okay?
Yeah.
So on one side you have R1 and D1, and on the other side you have like a wire connecting the 2 points together. Do you think that the LED
Yeah,
will
I have
turn on?
to, after like when we were testing a functionality test, I already submitted this in as my symposium,
Yeah.
but this need another revision.
Huh?
The LED will connect it to the ground, not to the 5 volt line. I fixed in my,
Makes more sense because,
so when I was testing, it was making a short circuit over there, and it was not allowing to have enough voltage through the IC. So
is it on right now? On your transmitter?
yeah,
Is it on?
yeah,
So you solved this problem, right?
yeah.
Okay, because
So I just give the.
if you keep it that way, the LED would never
Never.
turn on,
Yeah.
because it's a
So-
short.
Yeah,
And you know
I-
that the current prefers the short, right?
So
Yes.
I was not known to that, but I did it. But I fixed that in my.
Okay, now, what do you, like, the inputs AD 8, 9, 10, 11, what voltage do you provide? Is it a 0 or 5 volts? Or any
So-
other voltage?
Yeah. So if the transistors are in a cutoff region, so when you measure the voltage, it will be like 5 volt.
Okay,
So when they conduct, it will be greater than 0.7.
so what do you provide to the basis of the transistors then?
So if they connect, if the level is detected, then the base will get a 5 volt. It will connect with the line of 5 volt, which I am setting at the end of my.
Okay. The other question is about the choice of the TX and then the RX, the transmitter and the receiver modules. Did you
Yeah.
do a research on that, or you just went with the first transmitter
this is the-
receiver you have seen and, okay, let's use them.
Yeah, so this is my first choice of my RF modules. I haven't gone through any other RF, because these are for the project based on the encoder and the decoder. The mostly recommended was this RF module for the prototype purpose. But this RF module cannot be for in actual product which will be going to market
So, if I understand, you'll be using another type of
of RF module.
RF modules?
Yeah.
Or why didn't you use them in your project then?
Yeah, but yeah, the first day I started with this RF module, and I have get known about how it works, and so I have stuck with this RF module.
Okay, you should have done like proper research to find the right transmitter and receiver for your circuit, because you're saying that you have a range issue, okay? So, and this, if you have a range issue, then you should change the transmitter receiver modules, because this is a wireless, so it doesn't make sense to put the transmitter and receiver like very close, because you need to be away of the tank,
Yeah.
right?
Yeah.
If you need to
Yeah, we-
stay
we-
close to the tank, then it's useless, okay? The other question, you showed like some curves
Yeah, graph.
about the oscillator something. Yeah, what this means? Like,
So
do you have an oscillator
Yeah.
associated with the encoder and the
yeah,
decoder?
I have.
Can you show that on the schematic?
Yeah, so for pin numbers 15 and 16,
P60. Oh, okay, okay, yeah,
so those two are my resistive oscillator
okay,
for oscillating.
okay. So just curious, why does the encoder need an oscillator?
So the oscillator will be like once the data is updated from low level to medium level, the oscillator will just
Adjust the frequency?
Just means that this is the last question.
Okay, go ahead, sorry.
yeah. So for that it's the oscillator, the frequency oscillator. So for the frequency.
Okay, thank you.
I think we're out of time, so.
That's just, thanks everyone.
You can ask many questions.
Good. Okay, so we're about to enter the second presentation of the morning, and I'd like to make a specific mention that we have two guests at the back, at the very back row there, Mike Lawson and MJ Gadet from NAV Canada. So we're really glad to have NAV Canada back with us this year. We understand that they were attending online yesterday as well, so that's good. And we did have quite a few attenders yesterday afternoon. I think Mac had something to do with that, because I noticed there was like 24 online during his presentation, so.
Sorry, the family tree gets really long.
Yeah, okay, so that was good to see. So up next here we have Sonali Barreau and her automated dual zone irrigation system. Take it away.
Thank you.
Okay.
So good morning everyone. First of all, thank you for being here for my presentation. My name is Sonali Barreau and I'm from Electrical Alternate Program and my project name is Automated Dual Zone Irrigation System. Before I start my presentation, I would like to say that water is a very essential part for everyone's life. So I make project for reduce the water wastage. So this is the main concern of my project. So I'm trying to reduce the water wastage by implement this project. So in this presentation, I would like to cover objective of this project, concept drawing, project model I will show, project functionality, major components of my project, and technical drawings. So let's start from project objective. Behind my project, there is a story. So since my childhood, I saw that my brother he's working alone at farm, and every day he wakes up at the 5 o'clock at the morning, and he has to wake up early morning for feeding water to the farm. So I'm making this project and I'm experimenting on the small scale, and I want to implement the same concept on the larger scale at my brother's farm. So as my advisor said that by networking of soil moisture sensor, I can make this small scale project on the bigger scale. So this is my main object of this project. Let's talk about concept drawing of my project. So my concept drawing, you can see that on the front view there is a power switch and the LCD display. LCD display is showing the moisture sensor values and moisture condition from the soil. There is 4 LED indicator I used. One is showing this project is on or off, so it's a power indicator. Another is a pump indicator. When pump is running, that LED on and off, and there is a 2 zone. Right now I'm making for just 2 zones, so there is a 2 zone indicator as well, which shows that which zone needs water and which zone doesn't need water. And in the side view you can see that there is a power jack input from which I am supplying to my device. I'm using 12-volt adapter as a supplier for my device, and in the bottom view you can see that there is an outlet. From that I'm take off the wires for sensors, and when I have to doing programming to IC, I'm using that outlet. So this is my concept drawing for my device. This is actual view of my device, same as a concept drawing. You can see the power switch, LCD display, 4 LEDs, power LED, pump, zone 1, zone 2. So according the condition, it's showing, it's indicate the LED turn on and turn off. So this is actual view of my device. Now for project functionality. So my project works on 4 steps. So first, moisture sensor sense the moisture level from the soil, and then it's transfer the values to the controller. Controller triggers the water pumps and solenoid valves as per the soil moisture condition, and it controlling the water flow. So this basic function is on that my project is running. So let's talk about my major components. So first and very important component of my project is soil moisture sensor. I am using this type of moisture sensor, and I am using two because I am creating just two zones. In my brother's farm, I will make more zones, so I will use like 120 because my brother's farm is 1 acre land. So according to my calculation, it's 120 sensor it's needed. So by networking, I will do 120 zone. But for right now position, I'm just using two zone. I'm making two zones, so I'm using just two sensors, and it's operate on a 5 volt DC. It's giving value from 0 to 1024. It's giving value between this when it's operate. The another very important part of my project is controlling part. As a controller, I'm using Atmega 328. It has a 28 pins. It's include analog and digital both. So this is controlling my entire process of my project, and it also need a 5 volt for operation. And one more important part is water pump. It's operate on a 12 volt, and the ampere capacity is 65 milliamps to 500 milliamps, and it's also have a capacity to transfer 0 to 550 liters per hour. So this type of water pump I'm using for my project. There is one more important part is solenoid valve. I'm using two solenoid valve because I'm creating two zones. So it also operate on the 12 volt, and there is a LCD display. I'm using LCD display to show that which part needs water at what time. So it also showing that water moisture sensor value is high or low. So LCD display is also operating on 5 volt, and we can see the sensor values on the LCD. Now drawing and diagram. In that I will cover a block diagram, schematic and flow chart. So this is my project's block diagram. There is a two part of my block diagram. One is the power part. So first I would like to start with power. So I'm using a 12 volt adapter for powering my device. So 12 volt power adapter is connected to the switch. I needed two voltages for my project. One is 12 volt for operating water pump and two solenoid valves, and one I need a 5 volt for my processing control. So 12 volt adapter is connected to switch, and it's 12 volt connector. 12 volt I am giving voltage regulator IC, and from that I am getting a 5 volt, and another 12 volts I am directly taking from the after switch I am getting for my water pumps and solenoid valve. So this is my power supply diagram, and on the other side my processing diagram, it shows that there is a two sensors. So whenever the probes of the sensors, they are sensing the value from the soil as per the soil condition. It gives us some values to the Atmega, and Atmega Atmega sends that values, and according to that it's display on the LCD, and it also giving signal to the water pumps to off or on, and it also controlling the solenoid valve, which is zone 1 and zone 2. As a switching device, I use the transistor and relay, and there is a one float switch I used for giving protection to my water pump, because in the case of that there is no enough water in the water tank. In that case, it damaged the water pumps. So if I put a float switch, if there is no water, so in that case it create an open circuit and it protects my water pump. So this is my block diagram. And now my schematic of my project. There is 4 parts of my schematic. One is power on the top, like as I earlier said that from adapter I'm getting 12 volts to switch, and then after that 12 volt is coming on the voltage regulator IC, and that voltage regulator IC is giving me 5 volt, and that 5 volt I'm using for my for Atmega and also for power LED, and whenever I need like transistor, there I'm using my 5 volts. Also for giving Atmega a clock pulse, I'm using crystal oscillator circuit. So that is the crystal I'm using is 16 megahertz, which gives the clock pulse to my Atmega, and there is a 5 terminal you can see on the top. So that by that terminals I'm programming to my I'm using that terminals for programming my Atmega. So in the 5 terminal you can see that there is a positive, there is a negative, and there is a RX and TX, which is receiving and transmitting, and the one pin which is showing reset. So by that I can reset my program at Atmega. And after that you can see that there is a connection for LCD display. So from pin 14 to 19 there is a connection for D4 to D7 for LCD display, which showing the segments for my LCD display. Also there is a contrast pin. So by that I can control my brightness of the LCD. So you can see there is a 10K resistor I connected. So how I can get the 10K resistor value? So before that I put a variable resistor for seeing my brightness of the LCD. So then after analyze 10K is the perfect resistor, then I remove my variable resistor and I put a permanent 10K resistor, which gives me proper brightness of the LCD, sorry. And so it's also getting the 5 volt from voltage regulator IC, VCC, you can see that. And my LCD is the readable and writable both. And after that you can see that there is a 11, 12 and 13 pin, which I am using for my water pump, zone 1 solenoid and zone 2 solenoid. So from the Atmega, the 5 volt is going at T1 like transistor first, and that provide for 5 volt to my SPDT relay and relay coil, and my coil is energized, and I put water pump on the normally open side. So when relay coil triggers and get a 5 volts, that time it connect to the normally open side and it gives a supply to the water pump, And with that same concept, there is a zone 1 and zone 2. I use that same concept, and you can see that there is a one diode D1 and D6. They both have reverse diode, which I put there just because for getting protection from reverse supply. So for diode 1, I am using for protecting my relay coil when it's give me back supply, and there is a diode D6 when I get a reverse supply from my load side. So D1 and D6 is for just protection purposes, which I use here in zone 1 as well and zone 2 as well. So this is my schematic. And yeah, one more thing, there is a sensor. So I'm using two sensors. So both sensors, positive side, I merged it and I gave the 5 volt, and the ground also I merged it and I gave directly to ground. But the inputs of the sensors I gave to the ADMEGA on the 23 and 27. So by that way I connect my sensors with ADMEGA. And flow chart of my program and my project. So in the flow chart you can see that when I start my power switch, so moisture sensors sense the values from the soil, and it from the soil and from both zone, and it gives the signal to my controllers. And after controller there is two condition happens. So if the sensor value sense the value more than 740, then water pump and solenoid valves doesn't work. But if the sensor value is below 500, then in that case soil needs water. So in that case water pump also operate and solenoid valve open, and it provide the water to that particular zone. Also controller gives signals to the LCD for printing which zone needs water and which zone doesn't need water. So this is my flow chart. I updated this version which I gave you, that is different one. So that is my mistake. As a future aspect of my project, as I say earlier, I want to build this project in the real field at my brother's farm. So as a calculation, I said that 120 sensor I needed for 1 acre land. Also, I got one idea when I was working on this project, that I can build this same concept for providing water to farm animal, because right now my brother is giving water by bucket to the animal. But if I implement this same concept to provide a water to farm animal, it's possible. So I got this idea, and I would like to show you a real field where I want to implement this project. So this is my real field where I want to implement in future. There is another picture of my brother's farm. So here also you can see that there is animal who are they don't have any tank, so I can provide the tank and I can for feeding water to them. And at the conclusion, I would like to say that I researched in the market here. So I saw that for just one particular zone, if you are going to buy this same project, it costs you $200 or $250. But I completed this project in $150. So I feel that this is very less expensive and it's saving your money, saving water, and it's also reducing human effort. So I think my project is successful for satisfy this scenario as compared to market price. So that's it for my project. And this is all references I used for my presentation and for my schematic. And so now I would like to show a demonstration. So before demonstration, I would like to say that my solenoid valve is burned because I turn on my device without water. So that's why my solenoid valve is totally burned, and I try to get one more solenoid valve, but it takes time. So right now I am not able to show you the particular zones, but I can show as an indicator that my project is fully functional. So So here you are able to see that this is totally wet soil and this is dry soil. So right now it's showing that my power, my device is on, and right now my two sensors are outside, so there is no moisture. That's why its water pump is started. So if I put in the wet soil, which is this, it will show that moisture level is high and pump is stopped. But if I put in the dry soil, zone 1, and there is a one condition like high and low. There is a medium region as well. So in the medium region, soil doesn't need water. So in that case also my water pump is not operate. So this is the demonstration. If I need one just soil, so solenoid valve just one, zone 2 is operating. If both, then it's both. If I need one, then it's also one. And it's also showing that which zone needs water, which zone doesn't need water. So low, so both zones. Yeah. So this is demonstration of my project.
Thank you.
Start? You want me to go ahead? Okay. Can you take us to the slide where you showed the characteristics of the pump?
So block diagram?
No, it was before the block diagram. There was, you had mentioned each component and you
Oh,
talked about
this
the
one?
pump. Yeah. Oh, yeah, okay, yep. you're showing there, the pump is, has a range of output of 0 to 550 liters per hour. Does that apply to your project? Like, do you have a variable rate pump here? Does your project have the ability to pump less water if the soil is mildly dry, or more water if the soil is very dry?
So like controlling pump, like I can control the water flow. So I'm researching on that. So this pump is not varying the water flow, but for my brother's pump, I will do that research on it. But this pump is just same thing. It's not controlling the flow.
Okay, because I'm just wondering, when I read this here, it leads me to believe that you're able to adjust the flow depending on the need. And so I was just curious as to why that you're specifying a range, 0 to 550. Is it 550 liters per hour, or is it 200 liters per hour, or what is the actual number that you're getting from this project that you built?
So that same pump I got it. So from data sheet I put that value. So
Is the pump actually variable though? Or is it just on and off, you know what I mean?
it's on and off.
Right, so my question is, your choice to show a range here, why did you choose to put a range of 0 to 550 liters per hour? When it seems to me that that is not what's happening, it's actually a fixed value. So that's my question, right? Why the range?
It just means this is the capacity, like per hour how much it can transfer the water. It's not like controlling the flow of water. So it's not variable.
Okay.
That's my mistake.
So it should probably just say 550 liters per hour. Is that the actual volume, volumetric ability of this pump, or can it actually do 550 liters per hour?
Yeah, means in the testing I did it. So it's transferring 550 liter per hour water, but it's not controlling the flow, like
Okay.
how much this.
Yeah, okay.
So did you do the test?
Yeah.
You did, yeah.
Okay.
We didn't see any test results mentioned,
Yeah,
right?
test
So that's kind of what I'm getting at too. So we don't really have any evidence showing that it does 550 liters of water per hour.
Did you put anything on the report?
For
About-
testing,
about
yes.
the test?
Yeah.
You did?
For
Okay.
report.
I don't know about anybody else, but I have a few more questions. Do you have any questions
Well,
on this, or?
I'm just gonna, so everybody
Okay.
have any more questions?
Maybe go to the block diagram first?
Sure.
So we'd be kind of on the way there.
Yeah.
Yeah. I had a question about, unless you want to take this one. Okay. I had a question about the moisture sensor part of this. I see 4 probes shown there, but in your demonstration I only saw 2. So I'm just curious, where are the other 2 probes?
So probe means the leg of the sensors. So there is 2. So that's why it's a 4.
Okay.
Yeah. So probe means the legs
Okay.
sensor.
That I just find that a bit misleading. Maybe you're considering them to be 2 probes, but it's 1 unit, right?
Yeah.
Anyway, okay. Any other questions on the block diagram? Okay, we can go to the schematic.
Yeah,
I have some questions there too.
okay, let's go to the schematic then. Well, I noticed you're showing here two zone 2 LEDs.
Okay.
Yeah, so that is my mistake, that zone, this is for water pump, but I didn't update it. So zone 1 LED, it's a basically water pump indicator. And this is zone 1 and this is zone 2. So
I assume the
Yeah,
top one
that
was
is-
for the pump,
that is
the
mistake.
flow switch.
That makes more sense now, yeah,
Yeah.
okay.
My other question is, you had a external oscillator crystal for the Atmega.
Mhm.
Does the Atmega have internal oscillators that you could have used?
No. Actually, this crystal oscillator circuit, I found out from the Arduino Burn Boot website. So from that, I got an idea like I can do this and I can give the clock pulse to the Atmega. So
Okay.
Then how did you choose the frequency of that crystal?
on that website, it's showing that 16 megahertz crystal oscillator is good for giving controlling for 12 volt. So by that I found it.
In regards to D1, you had explained D1. I missed your explanation there. Could you explain that again, please?
Yeah, sure. So the D1 and D2 and D3, the three diode are in the reverse bias. So when in the relay, there is a relay coil. When some relay coil is giving back supply, so in that case, it gives protection. Like it gives protection to the system and water pump as well. So basic function of the D1 is giving protection, provide protection for back supply.
Okay, so what is D1 protecting?
So so if something back supply is come, it's remove the circuit and it's giving open circuit, and it doesn't give a fault to the whole circuit.
So let's go this way. So under normal operation, let's say that the pump is operating.
Mhm.
Okay, so you got the water pump labeled there. So the water pump is operating. Okay, which means what is true about the relay?
So I put a water pump on the normally open side.
Yeah.
So
So the pump's operating. What's true about the relay?
means, can you please repeat the
So
question?
the pump is operating.
Mhm.
So the pump is energized.
Mhm.
What is true about the relay?
So pump will energize when common SPDT relays common knob is on the normally open side.
Good, yeah.
That time pump will operate, otherwise it will not.
Okay, and what is required in order for the relay contacts to be in that position, into the normally open position?
So for operating that, it's need for relay it needs a 5 volt.
Which part of the relay?
For
You're doing well. Keep going. Yeah, I'm impressed with how you're answering so far. Keep going. So you said that in order for the pump to be on, the relay has to be in the normally open position,
Yeah.
right? What is required to put the relay in the normally open position?
So when transistor gives a 5 volt, that time relay coil will energize, and
Okay.
that normally close that connection, it will go this way and normally open.
That's good so far. So you're saying that in order for the pump to be on, then we have to energize the coil,
Yes.
right? So, and that is done via T1, is it there?
Mhm.
Okay, perfect. So now, this is my question. So that's a normal operation. The pump is operating, and you know it's supplying water until your soil has sufficient moisture level. And so during that time, relay K1, the coil is energized, as you said. What is the state of D1 during that time?
So in that case, it is reverse bias, so it will not giving, means it will not affect.
Very good. So it's a reverse bias diode. So it's actually like it's not there, right? It's an open circuit. Okay. So the moisture level in the soil comes up to the level that is required to turn the pump off now. Okay, so what you just explained all reverses, right? Everything inverts. So the relay closes, right? Goes to its normally closed, right, position, which means the pump stops. And in order for that to happen, what has to happen to the coil? In order for the relay contact to go back to its normally closed position, what has to happen to the coil?
It needs 5 volt. So
Well, you told me it needed 5 volt to go to the normally open position. So what's required for the relay's contact to swing back to the normally closed position?
12 volt. So on the common terminal, I
no.
gave direct 12 volt.
No, but you're missing my question. So what is required in order to cause the relay contact to swing back from normally open to normally closed? What is required to make that happen? What has to happen to the coil to cause the contact to go back to its
So,
normally closed
If
condition?
5 volt cut off.
Aha, so you have to remove the 5 volt potential from the coil, okay? So in other words, the transistor is going into cutoff, right? All right. And so here's my question. As the power is removed from your relay coil, what happens? And what happens involving D1?
So if power removes from relay coil, it goes normally closed.
Yeah, it goes, yeah, the contact go normally closed. What happens internal to the coil?
Yeah, it doesn't energize if it's not 5 volt.
It's de-energizing. So what's happening during the initial phase of being de-energized? The coil gets de-energized. What's happening during de-energizing of the coil?
So de-energize the water pump not work.
Let's talk about the coil itself. Don't just focus on K1 coil. What's happening internal to the coil as T1 switches from saturation to cutoff?
So coil terminal. I'm not getting questions.
Okay, what is a coil? What is it? What's it made of?
Wire.
Yeah, many turns of wire, right? And so, of the 3 basic circuits components, what does it look like? Does it look like a capacitor?
No inductor.
It looks like an inductor. Very good. So if it looks like an inductor and we remove power to the inductor, what is the inductor going to try to do?
It gives reverse supply.
Why does it do that?
Its characteristics for inductors.
Yeah, and it does that to try to do what?
For
What is the property of an inductor?
discharging.
So we know that resistors oppose current, capacitors oppose changes in. If we eliminate the other ones, you'll get the one I want, right? Capacitors oppose changes in voltage, right? Inductors oppose changes in
Current.
Current. So what's this coil going to do then? We have, how much current is there when it's operating normally?
1 amp.
1 amp. So the inductor wants to oppose the change in that 1 amp. So it wants to keep the 1 amp going.
Mm-hmm.
Okay. How does it do that? How does it keep the 1 amp going?
I don't know.
You said it. That's why I just want you to say it in this context.
Mm-hmm.
So you said it. What did you say?
For
It produces a voltage that is what?
coil.
Yeah, what does the coil do to cause the current to continue to flow it? Because you're right, inductance, its property is to cause the current that was previously flowing to continue to flow, at least for an instant,
Mm-hmm.
right? And then we get into LR time constants and all that. So how does it do that? How does it keep the current moving? Even though the BJT T1 is in cutoff? Internally, what happens? It produces a voltage that is in opposite polarity to what existed before the switch opened, right? Before the BJT opened, or when it cut off. All right, so the polarity initially would have been 5 volts plus minus, right?
Mm-hmm.
Positive on top, negative underneath.
Mm-hmm.
But the polarity is going to switch, isn't it?
Yeah.
Okay, it's going to be positive underneath, negative on top. How much voltage is going to get produced there? In order to keep 1 amp of current moving, how much voltage is it going to take?
5 volt.
I would say it's going to take a lot more than 5 volts, wouldn't you? Because where does it have to, under normal, like without the diode there, right? Okay, without the diode, it's going to have to produce a lot of voltage because it's going to have to overcome the cutoff resistance of the transistor,
Mm-hmm.
right? So it's going to be a high voltage. So what's D1 there for now? That's what I want you to explain. Why is D1 there?
So if high voltage comes on the back side, it will cut off the circuit.
It won't be able to go high, will it? What's the diode doing?
That here it's just for protection.
With the diode there, will there be able to be a high voltage?
Um,
No, why not? Because what's the forward voltage of that diode?
um,
0.7. It's silicon, right?
oh yeah, 0.7.
0.7. I knew you knew that. So if the diode has a 0.7 volt forward drop, then what is the maximum possible voltage that can exist across the coil when the coil becomes de-energized? It's a parallel circuit,
Mm-hmm.
right? So what's the maximum coil voltage then, because the diode's there?
So
You just said it a minute ago. Just say it again, and you'll get it right.
5.
0.7, right? Okay. So what happens to this 1 amp current now? Where does the 1 amp current go? Because you told me that the K1 coil has 1 amp immediately before the transistor goes to cutoff.
Mm-hmm.
So where does the 1 amp current conduct?
Across the diode.
Not across, current doesn't go across. Current goes through, right? Through the diode, right? In which direction?
Reverse side.
Hmm?
Reverse side.
Which direction, up or down?
Up to down.
Try again.
So
You can't have current flowing from up to down in that diode, right?
I put in the reverse bias.
If it's conducting, it has to be forward biased, right? So this diode actually conducts current from the so terminal 2 of K1 up through the diode and back down through K1 and up through the diode in a loop,
Okay.
okay?
Yeah.
And it's doing that for a very specific reason. Why is it doing that? What is it protecting?
Coil.
No,
No.
no. It's not protecting the coil. What's it protecting?
It's protecting. Oh.
If the diode wasn't there
Mhm.
and we got this huge voltage, it would be very high, okay? Which component is going to be damaged by that high voltage? Might not happen the first time, might not happen the second time, might not happen the 50th time, but maybe by the 100th time that this water pump turns on and off, what's going to fail?
Relay.
No, the transistor T1. Because what's its maximum voltage in the data sheet?
Yeah.
Less than what
Less
the
than 5.
what the inductive, this is inductive kick that we're talking about. okay?
Yeah.
So what's the name for G1 then? That action that you led us through here is a very specific action, and the diode has a very specific name. Do you know what it is?
Freewheeling diode.
It's a freewheeling diode.
Yeah.
I knew you learned that somewhere.
Yeah.
Okay, so I guess we're out of time. Sorry about that. I took all your questions away, right?
That's all good.
Okay,
So,
nice work. Okay, so welcome to our third presentation of the day. I would like to remind people who are sitting in the room that we do have these immediate feedback forms. And if you're not doing anything else during the presentation but listening, I'd encourage you to fill one of these out. For those who are grading, well, that may be a bit more of a challenge, but it's great for people to get these immediate feedback forms so that they know how they can improve and what they did well about their presentation. So without further ado, we have Sagar Dakin. I may not say that name right. Almost there, right?
Yeah.
He's honest, I like that. And his indoor climate monitoring system.
Yep.
Take it away, Sagar.
Thank you. Good morning, everyone. So I will start with an incident. Before coming to the Canada, we had a meeting with our immigration consultant back home. So he said that whenever you go to the Canada, make sure in your phone you have a weather app downloaded. I was like, okay, why? So when I came here and when I experienced my first winter, at that time I understand, okay, because every day you check your phone and you see what's the weather today, then you go out to the home. So everywhere you get the data, but it's for the all over the outside data. If you want to know what's the temperature in here, what's the humidity, so what do? So that's the indoor climate monitoring system. My name is Sagar Dakan. I am from EET Industrial Control, and this is Moncton. Mr. Metcalf is my advisor, and let's go. So first of all, I will give the overviews what is going to be there. So we will see the background and the objective of this project. Then I will go through the concept drawing, what was in my mind and how did it go, and then the block diagram of the project, then we will go through schematic, then I will explain the flow chart, and I had done some testing too, so I will talk about that too, and takeaway and conclusion. So let's start with the background and objective. So back then in medieval times, there were some people who would look at the sky, they will see the stars, and based on that calculation they will say, okay, what would be the data and everything. But as I said, we get our weather data every day on our phone, but the first daily weather forecast was done in 1861 by Robert Frisley in the Times London. So for that he had a set of 15 different stations, and he was using telegraph to give out the data every day. And nowadays we have Google DeepMind for that. So Google DeepMind is an AI from the Google, not the Google, actually DeepMind, because DeepMind was founded in 2010 in UK, and Google acquired that in 2014. So Google used that AI. So what does this AI do? It will monitor the 20 minutes data, and based on that data it will forecast next 90 to 120 minute rain forecast for that. So what are the general weather parameters when we talk about that? So those are temperature, humidity, pressure, wind, what is the visibility, what's the dew point, precipitation, and solar radiation too. But the thing is those are done for the global or local forecast scale. But when we talk about the indoor spaces, what do we have there? So for that matter, to know what is the temperature or humidity and pressure. So I made a device for that, so that can measure the indoor climate weather parameters. So now we will go through the concept drawing. So this is the latest concept drawing I had The measurement, I got it after I got my enclosure. I had almost similar thing in my mind, like it would be like 6 by 3. So for that, so in the front panel, so there is an LCD and a rocker on-off switch and a display change button. That's the momentary push button switch. The thing is like it is a wall-mounted device, and it is attached to a wall adapter to power up the device. And there is an external temperature sensor too. In the side view, I have put some space for the ventilation, so it can breathe in air and it can tell the data more accurately. And in the bottom view, there is the same thing, a way for the wall adapter, one for the temperature sensor, and the ICSP connector. So it is for like I use the 8 mega microcontroller here. So if in the future I want to modify a program, so I can connect it there. Now let's look at the block diagram. So the block diagram, we can say that there are 3 major sections. There is one is the power supply. This is the input sensors over here, and this is like processing and displaying it. And there is one user input over here. So in the power supply block, so there is an on-off switch. So yeah, so the power supply is the wall adapter, so it will get the 120 volt and convert it to 5 volt with the maximum current of 1.5 amps. And it is directly connected to the on-off switch, and from the on-off switch it goes to the voltage regulator. So the voltage regulator converts the 5 volts into 3.3 volt, that is the needed for my project. So here are the 3 different sensors over here. So the first one is humidity sensor. It runs on the 3.3 volt, so it takes in the air humidity. There is a barometric pressure and temperature sensor. So the thing is like the pressure sensor I used, it also measures the temperature too. So I use the one sensor for one device for 2 different sensors. So it can take the ambient pressure and the temperature as an input. And I put this in a different box because these 2 devices are inside the box, while the outdoor temperature is outside the box. So it is taking the outside air temperature. And here is the H mega 328P, that's the control of my device. And it is connected to the 16:2 LCD display. And all of them are running on 3.3 volt. And here is the display change button. That's what I named the momentary push button switch I have. And all the devices, like the 3 over here and one of the 4 devices, communicate with the H mega on the I2C bus. So that was the block diagram, and now let's look at the schematic. So over there, so the power comes from the wall adapter and it is connected to barrel jack. So barrel jack directly goes to the on-off switch over there. From the on-off switch is just a SBST rocker switch over there. Then it goes to the U1, so that is LM3940, that is my voltage regulator. So it converts the 5 volt to the 3.3 volt AC. Over here, so yeah, here is the EC74A2, so U2 is my temperature sensor over here. And it has 4 pins basically, one for the power, one for the ground, and 2 pins are for this SCLK and SDS. So those pins are for the communication with the controller. And both of these pins over here, it goes to SDS, that's pin number 27, and there's SCLK, and that's pin number 28, and both of them are pulled up through the pulled up register R1 and R2. Similarly, this is the U3 HIS7120. So that's the humidity sensor from the Honeywell, and it has same the 4 pins, 2 for the power of the device and 2 going to the controller. And here is the pressure sensor. It is also from the Honeywell, and it is a 4-pin IC similarly, and it goes to the controller via pin number 3 or 4 over here, and ST and SLK over here. Over here, this is the LCD. So the LCD also had the I2C function. Actually, the LCD I use can work on SPI and I2C, but I was using the I2C as the common factor to communicate with the controller, so that's why I am using only 4 pin of the LCD. And here is the PB1, so that is the momentary push button switch, and it is named as display change button. So it is connected to the interrupt 1. So the purpose of this switch is to change the display, as it says, because when I power up the device, it will show the temperature data first, and if I want to see the humidity and the pressure data, I'll press it with push button switch, so it will toggle the display. The same thing, if I want to see the temperature data, I will press the button, and I can see the temperature data. This is the ICSP connector. So pin number 2 goes to the VCC. This goes to reset pin over there. This is MOSI pin number 7 goes to number 17 of the controller. Pin number 4 goes to MISO of the controller. This is serial clock goes 5 to 19, and the ground pin over there. And yeah, one more thing. So the circuit over here is the debouncing, because the switch has the, when you press the switch, has the switch bounce so many times. So to reduce that effect, so so this is the switch debouncing circuit over there. Now let's look at the flow chart over here. So it is a pretty looks simple, but it's literally not that simple. So when we start the program, it will set up the system. So in the system setup, what happens over here, it will first initialize the interrupt, then it will initialize the 2-wire interface. 2-wire interface is the similar to the I2C, but it is not that much similar. I2C is from the patented by Philips, and TWI, 2-wire interface, is from Ekman. So just to avoid the copyright and the legal issues, they say 2WI. So it is initialized. After that, LCD is initialized, and after that, the sensors are initialized. And once the system is set up, it starts reading the data. So it will read the data, then processor will process the data and will convert the data in the required form, like pressure. So we are measuring pressure in the millibar, so it will convert PSI to millibar and vice versa, and then it will print the output on the LCD. So now we will look at the snippet of the codes. I think it is very hard to read, but I wanted to include a little more in here, so that's it will look a little smaller. So in the beginning, there are a library included there, and there are some pins, those are defined. Like TWI, NAS is when you want to read the byte without the acknowledgement, so it is defined for that. There are slave address. So for TWI interface, each device has the particular slave address assigned to that. So you have to include that address for the microcontroller, so it can communicate with the exact device over there. So LCD address, the temperature sensor, the pressure and humidity. After that, there are some definitions for the temperature sensors. So the temperature sensor has different mode, like configuration mode, standby mode, or normal mode. So whenever you are the first time you are programming the temperature sensor, you have to go into the configuration mode. And for my purpose, because I want to work it in the normal mode, so that's why I put it like 00. So if you put the pin number 00, it will work as a normal mode. So it is only one time thing. And these are the definitions for the LCD. What is the raw number and what is the raw 0 address and raw 1 address. So over here, this is the setup for the GWI. So it is initialized like it is the clock frequency is set to the 200 kilohertz, and this is the GWI start. So microcontroller is it works as the master slave over here. So microcontroller is the master, and the 4 other devices are the slave devices. So to start the communication, it has to put the start data on the bus, so it can start the communication with the particular device. So it's the TWI start is the start function. So similarly, there is the TWI stop function over there. So for the start and stop, so TWI control register, I have to set the interrupt, the start, and the enable bit to 1. So it will start the TWI communication. Similarly, when I set the interrupt bit, stop bit, and enable bit to the 1, it will stop the communication. And here is the write function over there. So whatever data you want to write on the bus, you read there. And similarly, and there is control register, you set the interrupt and the enable bit, and it will start writing the data on the bus. So here is a setup for the humidity sensor data. So for the humidity data, it has the precision of like to the 2-digit, but for our project we are only, because whenever you measure the humidity or when you say how much humid it is, so you say percentage, like 30% RH, 50, 70, vice versa. You don't say 50.5. So it will start reading the humidity sensor data, and the humidity sensor has one function. Like every time you want to communicate with the sensor, you have to wake up the sensor, because as soon as you are done with communicate with the humidity sensor, it will go into idle mode. So you have to wake up it every time. And after giving some delay, you have to start writing the address, like what address I want, what is the address of the humidity sensor, and then if you want to read what is the data, so it will read the data over here, and it will after reading the data, it will stop the communication with that, and over here it will convert the data. So this is the equation. It is given by the manufacturer. So how can you convert the data for your result? And this is the snippet of the main functions. It is for the after initializing everything, which was shown in the flowchart. Every device is initialized, so it will start reading the data, and whenever you want to show the data on the LCD display, it will go like this. First of all, I want to show on the line 1 indoor temperature. So what is the indoor temperature? So it will just go like that. If the temperature is less than 0, so it will put the minus sign for that, and it will display the data accordingly. And whenever I push the button, and on the top, I will show it when I will show the demo. So on the first line there will be pressure data. So it is indoor temperature and the pressure data. After that is the outdoor temperature data and the humidity data over here. And let's have a look of a little bit of like two-wire interface. So as I said earlier, so it is the 8 miles version of the I2C communication. So this is how usually it works like that. So there is a common bus going over there. So one line is data line and one line is the clock line, and you can attach the n number of device to this serial line. So I2C data over here, or you can say GWI, is the 7-bit address. So you can attach 128 different devices at the same time to one microcontroller. And both of the lines are pulled up through a resistor. Yeah, it requires the pull-up resistors. And let's look at the start-stop condition, like how the process starts and stops over here. So whenever the clock is high and the clock line is high and data line is going high to low, it will start the communication, like it will start reading the data or writing the data. And for the stop bit, clock needs to be high. So whenever the clock is high and data line goes from low to high, it will stop the communication. Similarly, on the high level of clock line here, data goes high to low, it starts the data and it repeats every time. Now I will talk about the testing I have performed. So I performed the testing on the testing device, like to check the data, like whatever data I'm getting, it should be right or wrong, or what is the its accuracy, or what is the offset. So I did the 2 calibration tests for that. One was done for the thermometer and one was done for the hygrometer. So hygrometer is to check the humidity level. So for the thermometer, I did the 2 tests. It is very simple test. One is the ice bath test and one is the boiling water test. So I needed 2 different data points for the thermometer, so I can know what is the actual value and what my device is measuring. So for the ice bath test, I put the thermocouple which was attached to the thermometer in the bucket of small beaker of ice over there with a little bit water in there. Put it there for 10 to 15 minutes and it should show the 0.00 degree. If you get 0.03, so 0.03 is their offset. So, and similarly, you put the thermocouple in the boiling water, and it should read 100 degrees Celsius. So the one I used, it was pretty accurate because, and it was accurately calibrated because on the both testing point, I was getting 0 degrees Celsius and 100 degrees Celsius. And for the hygrometer, I did the 2 tests for that too. So these tests are usually suggested by the cigar companies, because the cigar companies provide you a humidor, so it needs some kind of humidity for that. So they say if you have a hygrometer, you can use this test. So the one was the salt test. So for the salt test, the hygrometer should be with the little cup. Salt is put in a little bottle opener or something like that. You put it there with a little. It should be a little damp, 3 or 4 drop of water, and it should the hygrometer should be with the salt solution for at least 6 to 24 hours in a Ziploc bag. So after 24 hours, it should read like 75%. So that is the it should read for the humidity for the salt solutions. So based on that, I got the 72% for the salt test. So my hygrometer was off by 3%. And there is one wet towel test. So it is simple test, like you put your hygrometer inside a wet towel. It should be damp, and you put it for an hour 50 so, and it should read 100% relative humidity. If there is a little bit off, you can set the offset over there. So for me, I got the 100% in the towel test. So this was the data I got it there. So it says this is the actual humidity and this is the measured one. So on 100%, I got 100%. So when you get the 72% over here for the 75 of the actual one. So based on that test points, I got the line of the data and the slope of the line, and yeah, I got this line. So based on that, you can tell at what, if your hygrometer says X number of X percentage of humidity, so it should be actually Y% humidity in reality. And the pressure sensor, I could not test for that, but usually if you want to check your pressure data, you can use the government sources like it is like flightplanning.nme, canada.ca. So you can use their source as to test your pressure data. So the conclusion. So we have gone through what was the history of the weather data forecasting and what was the background for that. Then we went through the engineering drawings. Then I showed the testing and what I found. And yeah, I estimated the cost to be around $200 before tax, and I got it around $194 before tax. And there is still some scope to make it better, like if you can add more parameters like wind, or you can solar insolation data. You can add more devices, as we know, like you can add up to 128 devices. You can make it like dual zone or multi-zone temperature device, measuring device. And Yeah, because of the last time I could not calibrate my device, and this was the biggest learning I learned. Talk to your instructor when you are in trouble. So, this was the conclusion from my side. So referencing, and now I will show the demo. So, okay. Okay. Right. So this is the indoor climate monitoring system device I made for the this senior project. So yeah, it looks exactly like the concept drawing because I had something same idea in my mind going like what it should look like, and I found the similar enclosure for that. So over here, so I got here is connected from the barrel jet over here. Yeah, and this is the on-off switch. And here is the display chain button, and here on the right side is the pressure and temperature sensor. Over here is the humidity sensor, and the outdoor temperature sensor is connected over here in the another enclosure. So when I power up the device, so first of all it will say the indoor temperature and outdoor temperature over here. It is almost similar because it's almost in the close proximity, and over here it says 21.6. So it looks almost accurate, and whenever I press this button, it will tell me the pressure data and the humidity data. So humidity it says 29% here, and I got a device over here which says 36%, but whenever you use that graph, you get the exact data from the graph, and you can compare it with the whatever you get in here. And the pressure data over here, I can show you how can you do that. So here is the site I was talking about, flight planning inhibitor CA. Mr. Metcalf showed me how you can verify your data over here. So if I press this page over here, so at 202, so altimeter is what you are looking for. So here it says 30.36 inch mercury, yeah, 31.36 inch mercury. So whenever you can convert it using the Google over here, so it says 1028 millibar, and it's 102524, so it is almost there because the humidity sensor has the pressure sensor has the plus or minus 3% accuracy. So that was my demonstration. Thank you for your time and attention.
All right, thank you for that presentation. Do you have questions?
You can start.
I'm gonna start with the one thing you said at the end there that kind of had me a little confused. Can you just show the screen of your device again? There you go. So right now it is 29% relative humidity. But you said what is displayed, you need to reference it to your
Testing
graph.
device, because I didn't have much time to offset the data over here. I had a testing device. I had a hygrometer, so I tested like how accurate it is. So based on that data, I got a line, like using the two test points. So based on that test point, you can tell like for the actual humidity data, your hygrometer would show this much. This is your data. So you can adjust that data with the humidity data you're getting over here.
I'm still confused then. Because what is the relationship between the error between this device and your other device? How did you test that?
As I said, like for the soil test, when it is completely accurate, it will show the 75% relative humidity over there.
Yes.
So if you are getting 76 or 72, so that is your offset at
But
that
that's
time.
on your other device.
Hygrometer, yeah, it was on my hygrometer,
Okay.
but I didn't get the chance to perform the same test for the device over here.
Okay. That's fine, but the graph you have is between your hygrometer.
Hygrometer and the actual data. Yeah.
Okay, so, and then you're saying apply that curve to this. That's not right.
No, that's not right. Yeah, apply. You can have the relation between the hygrometer and your device, not the actual device, because.
Yes, but what is that? Where do you get that relationship?
So is it like your hygrometer is showing you 72%, so actually it is 75?
Yes, I understand that.
Yeah.
But
So
let's say that's saying 80%.
yeah, so if it is saying 80%, so you can make the same graph.
But did you?
But no, I couldn't. I didn't have much time. So for the humidity, I didn't have the time.
Okay, so you can't, that graph you have, you can't say, use that graph to relate to this then, because that's what you said, or I misunderstood. Okay. It's unfortunate because you could have done that electronically inside of that, and then whatever was being read was the correct value, right?
I had idea like if I can get it on like even if the prototype board, but because we are not testing the prototype board, so I was waiting for get the device done for that.
Well, we'll talk about that later. The other concern I have a little bit is the outside, bring up maybe your schematic at this point. Your outside sensor.
Here it is. Here?
Yes, so that one's connected to the I2C bus, right?
Yes.
So, how far away from your device can your outside sensor be connected? That I2C bus has a limit lengthwise. Did you look into that?
No, I didn't.
No?
Look at that. Yeah.
Because that's gonna be an issue.
Because I had a question in my mind, like, okay, we are saying like you can extend the wire for the outside temperature because it is a fixed device. You can, it's not mobile, right?
No.
So you just hang it on a wall and it will be there. For the outside temperature, I wanted to determine because if I want to see like at my home where can I put it there, so I needed at least 15 feet long wire.
How much?
15 feet from where I can put my device.
Yeah, that's pretty far.
Yeah, it was pretty far. So I was just concerned about like if that long wire is enough for like enough voltage level if I get at this
It's got
level.
nothing to do with the voltage though.
Yeah, so I checked it and it says like for 18 gauge wire it has 0.2 milliohm per meter. So
Nothing to do
so
with that.
yeah, it was. I can take care of.
So
that.
let's talk about what is the limiting factor. Maybe you don't know the actual distance, but, so I have a data bus here, okay, that is going to a certain distance, okay? As that wire gets longer and longer, you're right, the resistance increases, but that's not the factor here.
Yeah, it's not
What
much.
other parameters increase besides resistance for the wire?
When we increase the length.
Yes, so what other parameters increase based on length? There's resistance and what else? When you took your telecom, introduction to telecom course there, you guys talked about wiring. And we said clearly that no wire is a wire now, right? It's a system, it's a transmission system. So as that transmission system gets longer and longer, besides an increase of resistance, which you stated, what other two parameters also increase that are critical to you?
The clock signal.
The wire characteristics.
Okay.
So there's resistance, what other two characteristics?
Inductance.
Inductance and, what's the other one? Resistance, inductance, and starts with a C.
Capacitor.
There you go. Okay, so those are the other two, okay? If you go back to the clock and the switching and all that, resistance will have very little effect on that. What about inductance and capacitance? What effect will they have on high-speed switching? If you send a high-speed signal into a capacitive / inductive network, what can you expect to happen?
A noise. It will create.
Not noise, no. You guys love that word, but you don't know what it is. What happens? I've got a nice square signal, and I send it through an inductor and a capacitor. What can I expect to happen on the other end? Will it be nice and square?
There will be some distortion on the top. So
What else? When I go from low to high, will it be instantaneous? What happens? That slope will, it'll
some lag. Yeah. So it will little
skew, right?
Skew, yeah.
Right? So eventually there comes a point where I can't tell,
Which is the data.
no, what is a 1 and a 0 that defines the data, right?
Yes.
And the factor for that is, the defining factor is distance.
Distance.
So there's a distance where that no longer works, okay? So in your case, you should find that out, because you may want to put your head unit here, and there's the outside of the building, you may not be able to reach that.
If you get the data, it will be wrong. Like
Well,
the
it won't
water.
communicate.
Yeah.
It's not, it'll be wrong, it won't communicate. Anybody else want? I don't know.
Well, you didn't get to ask earlier.
Well, looking at your schematic here, U2, U3, and U4,
Yeah.
there's a capacitor C3 at the voltage input of U2. There's C4 at the input of U3.
Yeah.
Why is there no capacitor at U4? Is there a reason for that?
For the U2 and U3, it was recommended by the manufacturer, like you should have between these two pins. I tried to find out for the pressure sensor, but I couldn't find anything for that.
There's nothing on the data sheet to...
Yeah.
Okay.
Actually, on that topic of that area, JR1.
JR1, jumper one.
So what's that doing there?
So I don't have the PCB design over here. So for the PCB design purpose, I I had it was blocking. Yeah. So the ground line and the voltage line, it was blocking this data line. So I had to put a jumper over there.
Okay, but I don't think that's where it goes. I don't think that's where it goes on your PCB. You have two sensors that have 3v3 there,
Yeah.
and on top, right?
Yeah.
Yeah. Why, if 3v3 got to those 2 points on your PCB board, why would you need a jumper there?
Oh, sorry. Jumper 1 are for the jumping the power line. It was the power line.
Yes, I
Yeah.
understand that.
So it was, yeah, for
But
the
it
data
still
line.
doesn't belong there. You have it, I understand you needed a jumper, but it's in the wrong location. It should be in series with one of the 3v3s.
Yeah,
Here, okay.
because you're showing it's double fed,
Yeah.
right? U4 is double fed,
Oh, yes.
right? Or U3, which one, I don't know.
Yeah, it should be there. It should be there at all.
Yeah, okay.
One, yeah. Because on the PCB design, it
Yeah,
was
we're
going between
out of
these
time.
pin numbers, that's why.
All right, thank you.
Thank you.
Thank you.
Okay, so our fourth presentation of the morning is by Tuan Nguyen, and it's the solar heating room temperature controller. Take it away, Tuan.
Hello everybody, thanks for coming to see my presentation today. I am Tuan Nguyen, and today I am doing a presentation about my project, Solar Heating Room Temperature Controller. So, the presentation will cover 7 sections. It's the introduction, functional overview, technical description, the test and result, conclusion, the demonstration, and the questions. First, I want to introduce my project. I will answer 2 questions. What is this project and why it is chosen? So basically, my project is a solar air heater that can automatically turn the fan on and off by using the temperature controller. And I choose this project because I want to design a device that can heat up the room temperature by using solar energy. By using solar energy, it can save a lot of money by saving the electricity. And also, solar energy is an unlimited energy and environmentally friendly. Not like normal solar air heater. By using the temperature controller, my solar air heater can supply heat to the room automatically, and it can have the room it can by using it, the room can have the temperature at desired. Next, I want to tell you how the fan is controlled by the temperature controller. I will use block diagram to describe it. So this is my block diagram. I want to divide the block diagram into smaller blocks, so it's easier for you to see it. So for power supply, I use 120 volt AC to 12 volt DC to supply a 12 volt to the circuit and the fan. You can see the fan over here. My fan is a 12 volt DC fan. And as all the components on my circuit, it operates at 5 volt. So I use a voltage regulator to step down 12 volt to 5 volt. This 5 volt will supply the voltage for the temperature sensor and the sun voltage reference. The sun voltage reference I use to maintain and output fixed 125 volt. This 125 volt is used to calculate the other voltage reference. So I'm using the voltage reference V ref low, V ref up with S to control the fan on and off. V ref low is the lower limit, V ref up is the upper limit voltage reference, and the last one is the external limit reference. To control it, I use 3 variable resistors. By adjusting the resistors, I can have the voltage reference as I want. those voltage reference, VREF low, VREF up, and VREF X, they are going to be compared with the analog voltage from the temperature sensor 1, temperature sensor 2, in the quad differential comparator. Temperature sensor 1 is the temperature sensor inside the room, and temperature sensor 2 is the temperature outside the room. The quad differential comparator, it has 4 ohm amps, but I only use 3 ohm amps to do the comparison between those voltage reference. And after the comparison, the output voltage will go to the 3 input AND gate. This AND gate only open when all the output is high. And if all the output is high, it open and output a signal, a high signal to the MOSFET and channel. The MOSFET and channel here is act as a switch to turn on or off the fan. If there is some voltage to the gate of the MOSFET will close and allow current go through it. And that's the end of how the temperature controller control to turn on and off the fan. Next, I want to do a technical description. I am going to describe how my solar collector look like and how my temperature control box look like. So as you can see the picture, is my solar collector. I make the frame, a rectangular frame. The frame have the length for at 57 centimeters and the width is 39 centimeters. At the back of the frame, I use a plywood which have the dimension of 57 centimeters in length and 42 centimeters in width to cover it. The reason why the cover is larger in width in comparison with the frame because I want to mount the solar collector on the wall. For glazing material, I use the tempered glass, and for the absorber, I use the aluminum downspout. Each of the downspout, it has around 14 centimeters in length. I mount the fan inside the collector. And the fan is connected to the aluminum trial vent hose. This vent hose allows the air to go through the room. Here, underneath the frame, there is 4 holes. Those holes allow the air outside to flow in the solar collector through the vent hose. Next, I want to describe the temperature controller box. This is the top view of the controller box, the side view of it, and the front view of it. So for the top view, there is a hole which is 0.7 in the centimeter in the radius. This hole allows the temperature sensor to read the temperature inside the room. For the demonstration, I will use this hole and I connect I use jumpers to connect, to make it longer for the temperature sensor to test it. The balls have 7.5 centimeters in wide and 15.5 centimeters in length. This is a side view of the balls. I make 2 holes here. The first hole, I use that to connect the PCB inside the balls to the adapter. The bigger hole, the second hole, I use it to connect the fan and the temperature sensor outside the room to the PCB. The front view, I don't have anything to show. I just next, I want to do the electronics description. I'm doing it with my schematic. I'm using 2 schematic for this one. This is the first schematic, and this is the second schematic. To make it clearer to see, I divide those schematic into smaller blocks. So first, the 12-volt adapter will supply 12 volt to the circuit. You can see it over here. Between the power jack, which connect the PCB board with the adapter, I use a D2 diode. This diode is used to this diode is used as reverse polarity protection in case I swap the ground with the 12-volt supply. As I want to step down the voltage from 12 volt to 5 volt, I use the voltage regulator. Here. I use capacitor C1 and C2 with the regulator. The capacitor C1 is used at AC noise filtering, so that the input can be clean. The C2 capacitor, I use it to clean the DC signal from the output. This is the sun voltage reference. It's the 125 sun voltage reference. This one is in parallel with a load and requires 1 kilo ohms resistor to output 125 voltage. I use this one to output 125 voltage and maintain the fixed voltage. So when it output 125 voltage right here, the 125 volt, we will go to those 3 variable resistor. I use resistor R7, R4, and R9 to make a voltage division to calculate the voltage output from the variable resistor. So after the resistor, after I get the variable, the voltage reference at design, those voltage reference will go to the quad differential comparator to be compared and monitored. This is the quad differential comparator, but as I want to show it in detail, I use the OMAPs here. So those three voltage reference, we will go to the OMAP 1, OMAP 2, and OMAP 3 with the analog voltage from the temperature sensor. This is the temperature sensor inside the room. I used one capacitor here to make the clean the input, to reduce the noise from the input. The resistor R10 and C5 capacitor I use that for low filters, which is clean up the DC signal from the output of the temperature sensor. So the OMAPs, they work at the concept. If the input from the non-inverting input is higher than the inverting input, the OMAPs will output a high signal. So those three work at that concept. R1, R2, and R12, I use them as the pull-up resistor. If the OMAPs, if the non-inverting input of the OMAPs is higher than the inverting input, it will output a high signal, and those high signal will go to the AND gate. The AND gate is a 3-input AND gate, and this only output another signal if the three inputs are high. Here I use R3 resistor as a damper to smooth the process of open the process of open up the gate, the MOSFET. This MOSFET is acting as a switch to turn the fan on or turn the fan off. So if there is a high signal from the AND gate, the MOSFET and channel will connect the circuit. The fan, because the fan is outside the temperature controller box, I use connectors to connect it to the PCB. It is the same as the temperatures outside the room. The diode D1, I use it as flyback protection diode. So this diode is used to prevent the build-up voltage from the inductive load. In this project, is in the fan. So let's moving on the PCB layout. This is my PCB layout. In my PCB layout, I use 12 mil for the traces. As it is a one-side layout, I still have few chambers. If I connect those chambers at trace, they will disconnect the ground plane. So I decided to make chamber when I solder the components into the PCB. Next is the calculation. As I told that, I use the variable resistor with another resistor to do the calculation for the voltage reference. I will show you how can I do it. So from the data sheet, the voltage from the data sheet, the voltage output from the temperature sensor can be calculated by the equation on top, where X is the temperature in Celsius. And I use voltage division to calculate the value for the voltage reference. I do some equivalent, and I got this equation for the variable resistor. Let's make an example. So I want to turn on the fan at 10 degrees and turn off the fan at 35 degrees. So first I calculate the voltage reference output that need. This case, to turn on the fan, I need 0.6 volt, and to turn on the fan, I need 0.85 volt. So I applied the equation to calculate the values for the variable resistor. So to get 35 to turn off the fan, the variable resistor for the voltage reference upper limit, it is 2.125 kilo ohms, and for the voltage reference of the lower limit, it is 923 ohms. I do some tests and result output as well. The first test is to test the temperature sensor if it works at its correct range. So the expected range of working is 0 to 100 Celsius degree, and the tolerance is plus or minus 2 degree. I do some tests, and so the process is I place the temperature sensor on the breadboard, and I supply the voltage to the sensor. Then I use a multimeter to measure the output of the sensor, and I use the equation that I show you to calculate the temperature that the sensor read. So this table shows the sensor, show the temperature that the sensor read and the sensor that the thermostat read. And the difference between those two temperatures is around 0.5 Celsius. So it's still at the expected range. So there is no calibration need to do. The second test, I want to test the efficiency of the fan by using the airflow. So I use a garbage bag to cover the dryer vent hose, and I turn the fan on until the bag is filled with air. I do timing to see how long does it take to fill up the garbage bag. After that, I do some math to get the value. So the result is 0.99 M3 over minute, which is still at the expected range. So in conclusion, my project is 100% completed. I make the solar collector. I make the temperature controller box, and the controller box can turn on and off the fan automatically if there is some change in the temperature. I have some difficulty when doing the PCB layout, as at first I do the two side layout, but then I change it to one side. So when I have the board and I solder the board, I mess up it. I also brought some IC on the board, so I have to desolder the board to get the IC out. Then I use a lot of time to fix the board. So for a future aspect, I do have some improvement for my project. Right now, my project can only turn the fan on and off by reading the temperature. If I improve it, I will let the project read the moisture of the air as well, and to read the radiance from the sun as well, to decide to turn the fan on or off. That's it, the end of the presentation, and those are the reference I use for the project. I'm going to do the demonstration. So the fan only turn on when it meets two conditions. The sensor one is the sensor inside the room. It has to higher than 25 degrees and lower 35 degrees. The sensor two, which is outside the room, it has to higher than 25 degrees. This is my sensor one, which is outside the room. And this is my sensor 2, which is inside the room. Oh, this is my sensor 1, which is inside the room, and the temperature sensor 2 outside the room. So to turn the fan on, I will make those two sensors read more than 25 degrees by putting them into the hot water, not hot, it's just warm. So as you can hear, I turn the fan on when the temperature inside the room and outside the room is higher than 25 degrees. And if I still leave the temperature sensor outside the room, inside the room is higher than 35 degrees, the fan will be off. Right now, the temperature sensor inside the room is higher than 35 degrees. So let's cool it down to see if the fan is on. So when I cool it down by the cool water, the fan is on again. Right now, the fan is off again because the temperature inside the room read less than 25 degrees. Does not meet the condition. So I try to increase the temperature of the temperature inside the room to higher than 25 again. The fan is turned on again. So that's the end of the demonstration. So is there a question now? Okay, next question.
Can you bring up the slide for your schematic there? That one actually, go back. No.
This one?
It was, maybe you don't have that section. Do you have the slide, all your schematic on there?
There's two schematics.
I have one here, version 10.0, that controller -2 in the next, I guess your next schematic. Interestingly enough, your schematic doesn't reflect what I have here. In my schematic, you also have U1D that is not on your schematic.
Yes. The U1D is the unused amps.
Yes, I understand, but how come I have a schematic called schematic room temperature controller -2 dated May 19th, 2022, version 10.0.
H202.
2 of 2. I mean, my title block and your title block are identical, yet my schematic doesn't, or my schematic has more information than your schematic. In fact, substantially more, because there's different things in all kinds of locations here, if I look quickly. All right, I think you've got a version issue here. Anyways, I'll talk about my schematic, and maybe you can remember. Yes, you have U1D that is unused, and you indicate that you are doing, you did something with it, so you took the pins, which are not numbered in your schematic here, the non-inverting and the inverting pins, the input pins, you tied them directly to ground. So where did you come up with that conclusion?
Can you repeat that?
Your gates that aren't being used, your single op amp, not a gate, but op amp, in U1, so U1D, the input pins for that, input for non-inverting, input for inverting, you tied them directly to ground. What's your reference point for doing that, or why are you doing that?
So, if the inverting input is higher than the non.
No, I understand how that works. I'm telling you your unused gate,
Unused gate.
which is not on your schematic, it's on mine, but it's not on yours, okay? Your unused gate, you tied the inputs to ground. The inverting and non-inverting inputs are tied to ground.
Yes.
Why did you do that? What's your justification for doing that?
Because it's just an unused one.
So, sure, okay, so they're unused, but what made you tie it to ground? Where did you get the information that you should do that? And I'm not telling you it's wrong. I'm just asking you, why, what was the purpose of you
It's
doing
on the
that?
data sheet. I don't have any answer in my mind right now, but I can find out on the data sheet. and-
Yeah, well, I'll tell you something, on the data sheet, it doesn't tell you to tie it to the ground, not directly, okay? In a lot of ICs, such as your U6B and U6C, which is again not used there, that's on my schematic, not yours, okay, same version though. You did tie the inputs to ground, and if you go look at those data sheets, or the 7411N, it'll tell you to tie the inputs, the unused inputs to ground. However, the 11339, okay, tells you to do something with the inputs, but not to tie them to ground. You have to put a resistor in line with both, okay?
Yes.
Because you have to limit, ground, okay, is not just ground, it's where we dump a whole bunch of stuff, right? It's a low impedance location, okay? So, because of that, we have to make sure that the inputs can draw excessive current. And there is a limit to the current they can draw, it's about, I believe, 10 milliamps or so. So you have to put resistors in series with them for that to happen, okay? So, my point actually is not that, my point is, notice how you are missing information from what we have, and see how difficult it is for us to have a communication here, because your drawings are a means of communicating, okay? And if they don't match, well then you're looking at it from one aspect, I'm looking at it from another aspect.
While we're on the topic of grounding too, which is related, maybe you have this question too, but how many different grounds do you have?
Just one ground.
You have only one ground?
Yes.
Because I see 3 different ones.
Yeah.
Not necessarily on this diagram, but looking through everything that you presented and looking at the document package that you supplied, I see 3 different grounds. I see one reference that is marked just with the ground symbol, like the one on the, no, actually you've got one pointing off to the right in quadrant C8 there as well. So I don't know if that's a 4th one or not, but it's
It's a very unorthodox
Okay.
way of putting grounds.
but you've got that symbol, and then you've got the same symbol marked with GND as in the on U6A that
Is that
was there a
this
second
one?
ago. And yeah, you've got a lot of them marked as just unmarked ground symbols, okay? Then the bottom right here, you have A ground, right? It's marked A GND. And then on the other slide you had a minute ago, you have one marked just simply GND. So is that denoting several different ground reference points in that circuit, or what was the reasoning there?
Okay, so we explain this one first. The GND mark here is mean the GND of the TMP36. That's how I connect it to the ground. Just the symbol of the.
Well, typically, symbology-wise, if it's a pin name, it should be inside your symbol, okay? And the pin number should be on the outside. So you chose to go against the grain, I guess?
Yeah, that's confusing.
Reference designator should be external.
Yeah.
Yeah.
I have a question for this schematic here. I see a label for fan, but I don't see where it connects. The top right in quadrant 7BC there. Where does your fan connect to your schematic?
So my fan connect to the J2 J2 is a 6-pin connectors.
Oh, it's a connector.
Yes. So I use pin number 1 and number 5 to connect the positive and the negative terminal of the fan. 246 is for the temperature sensor outside the room.
No, the fan seems to be labeling either the source or the diode, in my opinion. like
It
the
should
fan.
probably have J2 and underneath it say fan, underneath that. Right? Because that's the connector going to the fan.
But it's not just going to the fan. It's
No.
going to the
Oh,
temperature
it's going to
sensor
the
as well,
Yeah,
so,
so fan shouldn't be there at all.
so maybe it should be some other label.
Here, R10 and C5, you mentioned that that was a filter,
Yeah, lower filter.
a low pass filter?
Yeah, lower.
To do what?
It's clean up the output signal.
The what?
Like, it minimizes the noise from the output signal and to make it a clean output signal.
So your TMP36 had a lot of noise on it? Is that what you're saying? No, I'm asking, your TMP36, the output of that had a lot of noise? Is that something that was occurring, or?
I have to check the data sheet, but even
Well, the
when
data
it
sheet will tell you if there's a lot of noise or not.
Okay. I think all the sensor, it has the noise. Everything has the noise. So to reduce them, I need to use them to,
Okay, so what's your cutoff frequency then?
sorry?
What's the cutoff frequency for your filter to reduce the noise? Because a filter to reduce noise, it has to band limit the signal. So what was your cutoff frequency for your filter? Where'd you get the values of 1K and 100 nano?
Well, I use 1K because
So how do you know where the filter's cutting off? If it's cutting off at a megahertz, 2 megahertz, 3 megahertz, you're probably not reducing very much noise. Okay, noise issues. And if it cuts off too
actually-
low, then you get problems of you're cutting off your signal.
I found this on like another website, but not the data sheet. So,
Which website?
well, I'm not sure because
If you're gonna reference other sources,
Yeah.
you better know what the sources are.
I didn't notice. So.
Who was the author in that, so in that website? Who was the source?
It just discussed on forum, so
Oh, because those are always
it's a
reliable,
discussion
right?
forum.
Those are always reliable?
What's that?
Those are always reliable sources?
A reliable sources?
They're reliable? They're,
You can trust them?
you can trust them, yeah?
Because I tested and it works, so it's a reliable. I tested.
Well, if you tested it, what's the cutoff frequency then? That's something you should have tested.
I didn't test the frequency.
Well, what happened if you turned it on and nothing worked?
Did it go over?
Jeez. How would you know to start removing it there?
Or
Maybe you had to remove the D1 or R3 or C6 or. Right?
Mm-hmm.
Anybody else?
You have 1 minute question?
Oh, I do have a question. Bring up your input to your power supply. You said that the other side of D2, the cathode side of D2 is 12 volts. Is that right? That's what it's labeled there.
Yes.
So on J1, what's going to be the voltage coming in there? What's going to be applied there?
J1 should be 12 volt.
Really?
The
What
power-
kind of diode is that?
What kind of diode?
What kind of diode is it?
Not sure what you mean, what kind of diode?
So 1N4002. So what's its forward voltage drop? What's its forward voltage drop?
Is that 1 here or the one?
The one up there, D2.
Okay.
Because over there you labeled it U5. What's a silicon diode voltage drop, typical?
I still not get your question.
D2, diode D2, what is its forward voltage drop?
It's for reverse voltage.
What is its forward voltage drop? What voltage does it drop when it conducts?
0.7.
0.7 volts across it, right?
Yes.
So if 12 volts is on the cathode side, could you tell me what's on the anode side of that diode when it is conducting?
11.3.
No. On the anode side,
The anode side.
on the left side,
Oh, it's 12 volt. Still 12 volt.
you can't have 12 volts on both sides. If it's got a voltage drop, you cannot
I
have.
think that's the design problem in this schematic.
What?
The
Oh,
12 volt should be.
Oh, it's not knowing Ohm's law and Kirchhoff's voltage law problem. That's what it is. So if 12 volts is supposed to be on the other side, then
Yes.
what should be there as a voltage?
On the other side, the diode.
So there's 12. When we've established you should have put 12 volts on the other side of the diode. That's fine.
Yes.
Okay. If that's true and the diode's conducting, where it says 12 volts right now, at pin 1 of U2, if it's 12 volts on the other side of the diode, what should be the voltage there?
Should be 11.3.
11.3 volts, yes. Because that diode, although it is for reverse polarity protection, when it's conducting, it's not free, right? It has a cost to it. Okay?
Yeah.
So it is incorrect for you to say that it's 12 volts there, right? Last quick question. You have let's look at R7 VR3 there, okay? So R7 VR3 act as what?
Voltage division.
Voltage divider, yes, okay. VR3 in itself acts as what right now?
VR3.
Yeah. VR3 in itself, the way it's wired, acts as what?
The voltage of the
No, VR3, as it is configured, acts as what? What kind of... Is VR3 a potentiometer at that point?
yes.
No.
No, that the voltage of the potentiometer.
A potentiometer is connected with its 3 pins.
Okay.
So now it is only connected with 2 pins, so that makes it a what instead? Starts with an R. A rheostat? Never heard the term rheostat before?
I think I heard about it.
Okay, so it acts as a rheostat, a variable resistor, okay?
Yes.
My question to you is, instead of doing that, could you not have taken VR3 and configured it as a potentiometer and rid yourself of R7 completely? Do you think that's possible?
No.
No? All right. Maybe you want to investigate that. It would have made a simpler circuit for you. Thank you.
Okay, welcome back to our afternoon presentations. It's great to have NAV Canada back with us this afternoon. Next up, we have Gojin Gao with his bank client's queuing system. Take it away, Gojin.
Good afternoon, everyone. My name is Gojun Gao. I'm a student of EET Moncton. My senior project lab is a bank client queuing system. Now, let me do a survey. Is there anyone know the experience about line up for the surveys? Raise your hand if you haven't experienced. Raise your hand. Everyone has the experience about waiting in line. Next question is if you found ahead of you there are many people, you need to wait 20 minutes. There are two choices. You line up on the line. Next choice is you call a ticket from the lobby manager, and you can find a place to sit or back into your car. Which one would you choose? If you choose the second one, or call a ticket, raise your hand. All right, everyone raise your hand. And your third choice, you can call a ticket by your cell phone. You can send a text message. You can get a ticket. Maybe you can get it at your home, on the road. If you like the third choice, please raise your hand. Right? Everyone choose the second one and third one. What you expected is what I worked last 6 months. So my presentation include introduction. Introduction is the queuing system, and background same as survey just like before. But my project concept, black diagram, technology description, and testing result. Last is the conclusion. About introduction, my bank client's queuing system is an embedded system. It's a virtual, we can use a virtual token replaces human line up for the service. And this is a device. This device has two method interface. One is the user or clients can use the text message to get a ticket. Another one is super easy. Maybe someone no cell phone number, they can press the button. Yeah. In the concept where here is the antenna. Can get the text message from the cell phone, and here is a button called service. Called token or called service. Called service button is for the manager. Called token is for the client. The background is from my personal experience. Last year, it is a pandemic period. Almost every day I need to line up to pick up my kids from the kindergarten, and one by one, and we have to keep the social distance and line up on the parking lot. Oh, very cold. I don't like cold. And there is one I couldn't forget the situation is I went to RBC Bank, and I found there's just 6 people ahead of me, and I'm waiting. there are three people is a senior man and senior woman ahead of me. That day is a raining day, very cold. My clothes is wet. I think ahead of me that people is waiting more time. They must be more cold than me. At that moment, I want to back in my car. I want, if I sat in my car, wait, oh, it would be more comfortable. But no that choice at the time. I hope in the future have more choice. It is a background. I chose this topic as my SPL. Most people don't like waiting. Pandemic period, we have to wait outside building to keep social distance, and bad weather makes that situation more discomfortable, and especially for elder clients. So concept, I want to build a device super small. Of course, in the market there are similar queuing system. There are user app. You need install an app in your cell phone, and you need Wi-Fi or something else to connect wireless. But my device don't need app, don't need install app, just use text message is okay. And for some people haven't cell phone, they can use the button. Here is the black diagram. As a typical embedded system, my diagram includes 4 sections. Of course, firstly, is the most important is the controller. And this controller should have input, output, it's easy to make sense, and should have input, output. Second, it should have communication. In my system, controller should communicate with 3 parts. But I want to choose Automega 328P. 328P if only one USART and one I2C. So I choose use USART to connect a PC. Use the I2C protocol to connect GSM model and LCD. Here I want to explain GSM model is a key component in my device, because just like the survey before, everyone likes the third choice. GSM is a global system. A global system of mobile devices. And here, this model includes an antenna, and we should insert a SIM card because it is like a cell phone can get message and send message. The fourth part of my block diagram is a power supply system. In this system, I use an adapter. Adapter can get 120 volt AC. That one can the output is 18 volt, 2 ampere. Because this voltage is too high for microcontroller. So after the power switch, there is a regulator. The regulator can output 5 volt for my system. I want to explain why I use extra computer and USR to USB. I will show we can monitor queuing systems data, and besides that, we can use this USB function to connect the printer or connect PC. This device will be a data collector. We can collect customer service data. We can maybe after 1 month or after 1 year, or morning, maybe 10 to 11 is a busy hour, and the bank can arrange much more tellers for service. It's a USB's potential function. Here is a schematic, my schematic. This one is a jack socket, the adapter plugged in here, and this place is 18 volt. After this connector, here is a regulator. Regulator is a LM 1084-5A. This regulator can output the maximum current is 5 ampere. And this one, the output is a fixed 5 volt. We can change maybe if you need 6 or 7 or other voltage with LM or 1084 not right. So here I saved 2 resistors, and usually here should have 2 divided resistors, and in this part is saved 2 resistors. Central is a Omega 328P microcontroller. Here is the microcontroller's power input. And there is a C3, is a capacitor. This capacitor can filter noises, maybe high frequency noises. And above this capacitor is a IC-SP. In my box, maybe I want to update software or something. You can programming from this part. Under it, here is a reset part. And this one is a code service button. This one is a PIN number or code token button. And both buttons by connected to the microcontroller. And this resistor is 0 ohm. 0 ohm resistor just let me do the PCB. And this side, here is pin 28 and pin 27 is the interface of I2C. And here is the 2 resistors, is pull-up resistors for the I2C bus. In this bus, there are 2 components. One is GSM, another one is LCD. And the next is a buzzer. The buzzer's function in my device is firstly, when you set up, it will be give a sound. When the manager calls service number, he will give a sound to attract attention. This buzzer. And the next one is a USB to USR module. And in this rectangle, this part is on my PCB board. Outside is installed in the enclosure. It is a software flowchart. Firstly, here should be a start. Firstly, we need an initial LCD, I2C, USART, and waiting serving array to 0, and initial interrupt. In my software, there are 3 interrupt. I will introduce one by one. Here is the main functions flowchart. Firstly is a print service number and token number to the LCD. Every staff or every client can see their number on the LCD. Then next is canceling button press. If someone code item maybe code double times, they get 2 tokens, but they just need 1. We can cancel 1. Yeah, here is the function of canceling oversized buttons, and the token number will -1. Next is SMS received from sleeve. Sleeve here is means GSM module. Microcontroller always send a request command to the sleeve, but if the sleeve get a text message from the cell phone, they can the GSM will send this message to the microcontroller. The microcontroller, the token number will +1, and then the microcontroller then send this token number and the service number to GSM. The GSM then send to the client. It's a main flowchart. Here is the timer 0 interrupt. Why I use the timer interrupt? When I want to monitor my queuing system's data, it does not update too much frequently. So here I set 2 seconds. 2 seconds the device send the data to the PCB. To the PC. And print SMS the message to the computer. This function 2 seconds just need to send one times data, can save a lot of resources for the microcontroller. And here is the second one interrupt. This one is the internal interrupt. If I press the button, it can exchange this interrupt. So here is the token button press. If it get token button will increase 1. This one is here should be service button press. Service button press is the service number will increase 1 and the button have a sound. If no button is being pressed, this place couldn't be screen. It also can save microcontrollers sources. This part is GSM, and it also is a sleeve station. GSM flowchart. Firstly, the initial GSM and I2C. then if the GSM gets the text message from the cell phone number, then it will save the cell phone number and save the message and send the message to the microcontroller, to the master. After that, the cell phone number, if the cell phone number not clear, here is the not clear, and it gets the message from the microcontroller to conditions. And will send the number to the it will send a text message to the customer's cell phone. It's a flow chart. And here is some program. This program is I called it in MPLAB because I involved a lot of libraries and sub functions or subroutines here. It includes IVRIO, pseudo, string, and interrupted or delay. And here is I2C master, and about LCD's libraries. And after that, here is here's some routine token string. Oh, sorry, should be here. Button sound subroutine display on LCD length. It means string length. And string insert. I need to send a message to the customer's client, and every time I just need to insert different numbers. Maybe this one is 2, next is 3. This is a string insert function. Next is interrupt. This page is introduced how I use the I2C protocol. This morning, Sigurd have introduced I2C data frame. I just introduced how can you use it. In this rectangle, it is a subroutine. It means I2C transmit function. Here is the address. It means the sleeve address. Next is the data. What data would you want to transmit this data? How many? What's the length of the data? And if I2C started, here is the address. This address should be same. Then add I2C write here, because here is the transmit. Transmit is it means write to the GSM. Next is transmitted data one by one. If the length is changed to 0, and there is the I2C stop command. It is a subroutine. In this next part is in main function. I code it. I just use one line code it. This line. I code it. I2C transmit. Then for shift 1 bit. Next is the data I want to transmit. This data just two numbers. Because I want to explain why here is a 4 shift 1 bit, because in I2C protocol, the address number is 7 bit. 7 bit can 7 bit is 128. It means the master can control or can commit with 128 slave stations. In my system, the address, the GSM address is 4. If we write 4, the GSM can work. We should move these 4 to the LSB byte, then left LSB for this one, for I2C write. This is 1 byte. Here's I2C protocol and my applications. And next, I want to introduce about the debounce method. I have to say I met a lot of problems about issues and about the debounce method. I researched 3 methods. Of course, firstly is use software to solve it. Secondly, here is the button. Second method is hardware. Here is a resistor and a capacitor can attract high debounce. And the third one is use of flip-flap between the button and the microcontroller. At the overclock, I want to simplify my circuit, my PCB. I use the software method. Software method, and I put this function in the internal interrupt. Here the internal interrupt if PD2 is one external interrupt. If this button is pressed, delay 6 milliseconds, then I check if the button always pressed, then the button is pressed, will do this function. This function is the service number will +1, but buzzer will sound. Here is a while compare. If the service number less than token number, it will increase. If the service number is equal or greater than token number, it means no one in the queuing system. So it doesn't need to include numbers. Next, I want to introduce my PCB and my encoder building. This one is my PCB layout. It is a 3D view. I draw my schematic and PCB layout by KiCad. KiCad is a very good software. It's open source. And it has a 3D view function. You can view this side, from any aspect. This one is printed by Mr. Laguerre. And I drilled. I have to say here I made a mistake. I drilled use 0.9 drill. The drill too big, because if the hole big, the pad will be small for soldering. Unfortunately, I told many classmates, and I think they will they have avoided this mistake.
You have 30 seconds. You have 30 seconds.
30 seconds to wrap up. Yeah.
To your conclusion.
Oh, sorry. And here is the power consumption testing. I use the current probe and verbal print to measure the voltage and current and get the maximum power consumption is 4.8 watt. Here is the conclusion. My conclusion is that the user can get virtual token by pressing button or sending message. The manager can manage it by calling service number. To the total cost is around $300. The advantage, clients can take a token by SMS, and on-site or off-site.
Okay, you have to stop. Thank you. You're over. So if you want to do your demo, that's fine.
Then this is my device, very small. Setup is very easy. Just plug in. Yep. What's on? Sorry, I can't use this camera. Now it is
Is it displayed on the screen on the laptop?
The camera is it on the laptop?
On the laptop screen, is it on there?
No, because we see the icon of the camera. That, yeah.
That's okay. I don't know, he's got it duplicated.
I think it's the type in the search bar for camera, maybe you'll see it there.
that's okay. So here.
Yeah, there's an extra texture receptacle there, you're okay?
Yes. My device back panel, this one is a buzzer. Here is a USB port, and this antenna. Here is the power switch. This one is a check socket. This front panel, here is a token button and LCD service button. Power on. Yeah, set up. If I am on-site click, I can press it. Oh, sorry. Why? Got too much. Oh. Oh, sorry. Why too? Now, there are 4 people in the queuing system, and one is getting the service. And I send a text message to it. What it mean?
Maybe the coverage is not great.
Oh, I have tried many times in the lab and in my home, but
Maybe turn it off and.
yes, usually it can get a message and include the number 4 will increase 1 and it can get your token is 5 and the third one is 1 and you need to wait how many minutes? 5 minus 1 and times a unit your unit time. Yeah.
All right, I
No.
think we're trying to that point there.
Yeah, we got basically 10 minutes to do questions. Yeah.
No.
Take it away there.
Thank you, Sergeant.
Oh, I'm sorry.
No, that's fine.
The short time is.
Yeah.
Could you bring up your schematic, please?
Oh, yeah. Who can help me turn off the camera? Can help me turn off the camera? I don't know how to turn off it.
The icon's in the lower bar there. If you right click on it, you should be able to.
Hmm? But I can't use the.
Or if you click on PowerPoint, it'll bring your PowerPoint back up.
Your cursor is on this display.
Yeah, he's on the wrong display, he's extending.
Schematic?
Yeah, your regulator, U1, you have D1, a diode there, 1N4000 series diode. What's the purpose of the diode and should it be there?
On this diode, I put this diode is to protect my circuit. If there's if there's some high voltage or maybe from outside, from external, it can protect this regulator.
Where would the high voltage come from?
Just in case.
No. Where would the high voltage come from? Let's say we're gonna build 1 million of these. That's a $2 diode.
Yeah.
It's $2 million right there in cost, right?
Oh, yeah.
Okay, so you need to justify that diode a lot more than just in case.
Yeah.
So what is it trying to protect, first of all?
Protect the regulator.
And what is it trying to protect the regulator from?
Yeah, if the output point have the high voltage,
What kind of high voltage? High voltage compared to what?
high voltage compared to this point, output point to compared to the input point.
Okay, so if there's a higher voltage
Yes,
on the output.
yes. This diode is should be all free volume diode. Yeah.
No, that's not what that is. So if the output of the regulator has a higher voltage than the input of the regulator, what's gonna happen? Let's ignore the diode for a second. What would happen?
The regulator will be burned.
Well, what? Will be burnt? Why? Why?
Because the V out, because this point just can be as output. Inside the circuit can't be as a put in.
Okay,
Yeah.
but what would make it, that's not the reason why that's there. So, you're right that the output cannot be larger than the input. What condition could cause that to happen?
What condition?
What condition could cause the output of the regulator on pin 2 to be a little higher to the ground,
Yeah.
be higher than from pin 3 to ground?
In this case, in this device, I think maybe I don't know. I just find in the data sheet of the regulator, and the diode can protect it, so I designed it.
Yeah, but it also says, quite clearly because I remember this,
Yeah.
it also says optional.
Yes.
So I'm asking you to justify the non-optionality of your, I don't know if that's a word, of you applying it, okay?
Why are you opting to spend $2 million?
Yeah.
Just in case.
Just because, like, you know.
Let's imagine this scenario. Let's say on pin 2, that capacitor C2 there is more than 10 microvolts, or microfarads. Let's say the rest of the circuit connected to that amounts to 10,000 microfarads. When you, at the input,
Yeah.
inadvertently short the input by mistake
Yeah.
in that condition, what would happen? You would have a lot of voltage at the output, very little of it in the input. And that means through the regulator, you have the potential for current to be pushed back through it, okay? There is a diode inside of it that actually protects it from that happening, okay?
Oh.
But
Yeah.
it only protects for something like 10 milliamps for, I forget the time's in
Yeah.
microseconds, it's really short, okay?
All right.
So the manufacturer tells you in the spec sheets, be careful, if you have the danger of that happening longer than or more current than, okay, you should put a protection diode like that in there to do that. But again, only if the condition applies. In their case, they specifically tell you it's something like, I forget there off the top of my head, but it's something like it's like a millifarad, okay? It's a very large capacitive value, okay?
Yep.
Your circuit definitely does not have a millifarad worth of capacitance on it, okay?
All right.
So in this case, you would not have had to put the diode in, okay?
All right.
Although it does tell you, hey, you know, they're telling you to put it in, but they give you, they tell you what conditions you should put it in and when you shouldn't. And in this case, it doesn't warrant it, okay?
All right. Okay.
There's a lot of people that do like you though, they just toss it in, they toss it in, right? But if you're gonna go into the business of manufacturing things, tossing things extra costs a lot of money, right? So you gotta be able to justify that, right? Anybody have anything else? No? Is there some time?
We got a minute.
R6, where's R6? R6 in line with the buzzer. Why is R6 in line with the buzzer?
Oh, here.
Yeah, why is that there?
Too loud.
Too loud, oh, as simple as that.
Yeah.
Excellent answer,
Yeah.
excellent answer.
I tested it in my home. The sound similar smoke detector. Why doesn't like it?
Just a follow-up question, I love your answer.
Yeah.
Just a what other way could you have made it not as loud, based on the microprocessor? So what other method could, let's say we say we're not gonna put the resistor in,
Yeah.
what other method could you have used to make it?
I can change the frequency. Yeah.
No, frequency doesn't have anything to do with amplitude directly, I mean, our ears are whatever. What about modulating the signal? What kind of modulation technique do you know that you learned?
Sorry. Oh.
Pulse width modulation? Remember pulse width modulation? You vary the width of the pulses, and the average value would run the buzzer, right? So you could use pulse width modulation on the Mega 328 because it actually has outputs that are pulse width modulated. You can't actually use them. And you could use that, and then you could actually have a volume function where you could have controlled it that way too. Okay, but that's a quick and dirty way of doing it. It's fine. Okay, thank you.
Thank you.
And finishing up the day with our last presentation here is Sandeep Kabir with his AC motor soft starter. Go ahead.
Thank you, Mr. Brown. Good afternoon, everyone. Thank you for being here on the second day of Symposium Week. I'm going to show you my senior project, which is an AC motor soft starter. And I'm going to talk about all the ins and outs about the project, how I came up with it, how I built it, and all the procedures with it. So I'll start my presentation. So I am Sandeep Kabir, EET student, alternate pathway. And this is the discussion that I'm going to talk about today about my project. Starting with a little bit of history, how my background came about this project. So in the year of 1886, the first DC motor was introduced by William Sturgeon, but it was enough to drive small machineries, but it wasn't enough for the use that we needed to do for the vast supply of the load. However, just a year later, in the 1887, Nikola Tesla built the first practical version of first AC motor. He built it, but it wasn't until the year 1892 that the first practical version was implemented or created with the assistance and the help with the Westinghouse engineers. But the people at that time was not ready to accept the AC motors because it was tagged as a very dangerous machine. Even it used to call it killing machine. So to urge to make it safe for human use started from that period of time that we need to make it safe. And with my project, I'm trying to do similar to that, to make it safe for use and protect it from the equipment that will be connected to it. So first of all, that I would like to talk about why I need a soft starter. Well, so a soft starter protects the motor from getting to overload conditions or a sudden surge of voltage current. So when we connect a motor to to the power, it takes a surge of current at the initial stage, which is higher than its requirement to start up. So a motor is not completely operational until it reaches a certain amount of RPM, rotation per minute, which is typically around 1800 RPMs. But it still takes that instantaneous current or voltage at the startup time, which sometimes creates damage to the windings, could cause various incidents like accidents. However, with the help of a soft starter, these problems can be reduced to some extent. What soft starter does, it makes like I like to call soft starter a friend of AC motor, because it helps to extend the expansion of its life to run for a longer period of time that would typically run without one. So this is just a small picture of my device, how it looks, and I will talk about now how a soft starter works and functions to the motor. As I already said about the soft starter is a friend of motors, like it acts as a friend to make it safe and protect it from being damaged or causing any kind of problems. The purpose of this device is to reduce the strain put on the motor during the typical power up phase of it, and as it protects from the initial surge that enters the motor instantly. And to accomplish this, what will soft starter do? That it will slowly and gradually increase the voltage to fulfill or make the motor reach towards full capacity for the rotation. And this allows for a smooth acceleration of the motor to run up, and the machine as a whole, as well as if some kinds of overload condition or over voltage condition occurs, the stop starter will stop supplying the voltage to the motor, which will protect the work environment as well as the equipment. So why building a soft starter? Well, the reason of my coming up with this idea is a little bit out of curiosity and personal. As I come from a South Asian country, most of the supplies to our households are around 220 volts to 240 volts. And when I came here, northern part of America, and I see the household voltage are around 120, and switches are also upside down than our part of the world. So that made me kind of curious that is it the equipments are weak here that doesn't need that much of voltage? What is exactly going on? So it took me around 2 years to understand the differences between that part or here while the duration of the study. And also at the same time, it can protect the machinery, so people who are using high voltages to the supplies to their equipment can be reduced the strains, so they do not or will not require to have that like risk of using high voltage equipment at their homes, or even if it's outside, who are not professional trained to use some motor kind of projects, motor kind of equipment, sorry. So it can be used in various places, or various ways, as we speak, like mostly the induction motors, fans that has the motor connections, water liquid pump, as so do I speak already that I had this idea from the background by witnessing the differences between South Asian countries and here, that the pumps and the motors are also used in various fields by the farmers, but they have to go through various certain problems about the start of their pumps to fetch water to their lands. But it can cause that damage to their motors as well, because they are also using that high voltage to supply. And it was kind of like a process to use it is very simple, so it's very accessible to all kind of people who would be required to apply to their loads or the high motors. There is an alternative, as we have learned about the VFDs, which is variable frequency drive, which can run a motor, have changed the motion speed and everything on that. But the VFDs or variable frequency drive are not very easy to use for mass people, because we need to learn how the functionality of it works. So as I have mentioned earlier, that why I wanted to make up it for easy access, VFDs cannot do that part for those people. For example, as I said, the farmers, if they want to apply to protect their motors or the pumps with the soft starter, if they will try to train them VFDs, what's going to happen to the crops? So they needed a very easy access, a very easy accessible product or device that can protect their pumps as well as their working environment. And also, there's another easy, good, positive thing about the soft starters, that it is less expensive than the VFDs. Initially, I proposed to go with the projected cost around $300, but I was about to cut the price, or when completed, it was less than its half. So it was quite a bit of changes, and the expenses cut off from the initial expected stage of the project. So this talks about the functional overview with the help of a diagram. And this diagram, the block diagram consists of various blocks that I'm going to talk now, and step by step of each. Okay. So the first block is a 120 volts supply to the device, and that AC that passes through the next block, which is a step down transformer, and it significantly reduces the voltage to an amount that passes through all the other components inside the device and goes to a rectifying bridge, and that consists of 4 diodes to rectify the AC input. And from the rectifying output, there is the voltage is divided in 2 ways at the same time. One of them are zero crossing detector, the other one is a voltage regulator, so which is fed by the previous block of rectifier or rectifying bridge. In zero crossing detection, or zero crossing detector detects the zeros of the rectified full wave signal, and they send those pulses to the following block of control circuits. And okay, from the voltage regulator block, an inverse exponential signal is received, which has a peak of 12 volts and drops down, gradually decrease to 0 volts for the control circuit. Now, the control circuit here is an op-amp comparator IC, op-amp amplifier, or op-amps as we speak, which is an LM339. So how does this part of the circuit or the block works? I'm going to talk now about it. So from its inverting terminal and non-inverting terminal, which is both of these supplies, it's compared the values of voltages and outputs and the differences between them. In my case, of the op-amp operation or circulation of the circuit, the output from the output of the voltage regulator is compared with the zero crossing detectors at the same time. The control circuit block modulates those sets of voltage, as I already mentioned, that how it's compared, and then it runs to the triggering circuit. As both the outputs change over the time, the control circuit block modulates those sets of voltage, and to perform the to run the operation or power up the control circuit, I have a 12 volt constant DC voltage that power ups the circuit, the component all the time, and that's why the triggering circuit here is the next block, and the triggering circuit blocks gives command through the transistor. In my case, is a triac, which should give the pulse when it should be opening, when it should be closed, and in my circuit I have both kind of loads. This side of the arms are DC, and this directly goes to AC. So I need a differential component that difference or keeps those connections apart. And in that case, for that to address that issue, I have the component which is an opto isolator or optical coupler, as we say, which is an MOC 3021. And for my case here, I have a startup time to 7 to 10 seconds typically to give it a smooth start until it reaches the full capacity, and the motor should be coming back to the full torque in that duration of time that the delay converted, and then it moves to the load, which will be connected to the output terminals of my device. And here is the schematic, and previous block diagram I put up, I showed all of the steps. So just to identify that this would be the step down part of the transformer that will be delivered by the AC connectors, and coming up to the rectifying bridge. Zero crossing detector, however, an issue came up. I tried to use an LM324 IC, but when I apply those to the breadboarding, it wasn't giving me the zero crossing signal, or it wasn't detecting good enough. So I had to come up with this part of the circuit which works as the zero crossing detector, and then the following goes to the supply goes to the other comparator IC LM339, and at the same time the voltage regulator works constant voltage of 12 volts, and this voltage regulator decreases the voltage with a period of time from 12 peak to 0. And the opto-isolator or optical coupler is differentiating the DC part of it here, and the AC part of the circuits are here, which is eventually laid and fed to the load output of the terminals. And for the safety, as I said, that this device will protect for any kind of overload condition or over voltage condition. This fuse will disconnect as it exceeds the amount of current or high voltage that could damage the motor connected to the device. This is the schematic, and these are the part lists that I have used to complete this project. And as can be seen, and it's very small to read, but the part lists are supposed to be in this order. So the pricing is showing here is around $131.81. Again, which is more or less than half than it was projected at the starting of the project. Now, test results. I have run 2 tests about making or witnessing the outputs of the signal coming out of the device, and as you can see that there has been 2 types of results showing on here. One is the simulation results, and that's the actual result that was performed here in the lab. So in the simulation results, in starting of the stage 1, when I run the schematic or run the circuit, it was flat, and gradually it's changing the cut-off, cut-in, and over the period of time it's turning into full 180 full wave signal. And as expected, to run the test while in the complete enclosure, the test results came exactly the same, and as can be, both are similar to each other. As expected, I want it to be smooth startly, and then it will reach its full capacity at the end of the completion of it. So conclusion of here is, I found out, or takeaways from me trying to do this project was, simulation is not enough, it's just the beginning. And I did the simulation, I did the breadboard, 80% of it didn't work. So I had to change every component to test what was going wrong, how it changes, and eventually by doing more troubleshoots, it was successful as expected from the beginning, and we projected it. And of course, in the furthermore, I would like to make it more affordable for all types of equipment, so that can be used easily, like the various loads, high loads or high horsepower motors I'm talking about. Now, following through, before the demonstration, I would like to show the concept, how it's looking, the looks of the device. Here, as we can see, here is the push button, that is the switch that will actually turn or start the supply between the load and the supply voltage. And these 2 ports are terminal jacks that will be the place for the motor to be connected. Once we start plugging with the extension cord to the wall, and eventually start the push button, the supply will be moving to the motor gradually, and as mentioned earlier, within the 5 to 7 seconds, typically the motor should start up to its full capacity. And yeah, these are the references that I have used to complete, and more references are also added to the final report. Okay, so that concludes my presentation part. Now I'll move forward to the demonstration part here. For the demonstration, I have connected the camera to the ammeter, as can you see? Can you see now? Okay, so when I plug in, for this demonstration there will be two steps to do it, one without the soft starter, my device, and one with this soft starter. So we can see the differences between both of it. And I will go and connect the plug, and we'll see there will be a sudden surge of current to the ammeter here. And the fan, of course, here will be instantly start up. You see a curve? Were everybody able to spot the sudden surge of the current?
Yeah, well, it kind of bounced up.
Yeah, kind of the sudden surge of it. So now I will connect it to my device and show the differences between them. Okay. Okay, now once I press the switch outside the device, as I already mentioned about the startup time, you can see the gradual increase, and the fan is also gradually starting up instead of sudden start. And closing it will shut off as well. So that concludes my demonstration and presentation. I'll be taking questions if anyone have.
Who wants to start?
Well, I'll start with an easy one. Could you go to your schematic?
Yep.
First of all, what program did you use to draw the schematic?
So to program this schematic, to run this schematic, I use Proteus software.
Does
And-
it, that's fine, does it not have North American symbology available?
Unfortunately not.
So then why did you use Proteus for in North America?
So
In the course that teaches you how to do things for North America?
Yep.
So I'll point out the resistors, the capacitors are not acceptable. And I'll also point out that that's not an acceptable SPL frame and title block either.
So when I started to design the schematic or the circuit, I tried to use Eagle and Multisim as well. And as I consulted with my advisor, that some components that I'm hoping to use or trying to use was not finding it easy, since I had a little bit of experience using this software. So I asked for my
So Proteus isn't used in North America at all?
I'm not aware of
I
that.
think it very much is, yes. I know
So-
several companies, and I'm pretty sure that the libraries are there, because you know what? You could have used, for example, Eagle, and if you use some of the default symbology, it would have been European symbologies too,
Okay.
okay? So don't blame the software, I'm not blaming the software, blaming you for not taking the time to select the proper symbology.
Well, I can get back to you doing the, like, since I purchased this software, I can contact them and verify that if the cert exists. So my knowledge,
It's too late now, this is your project, this is the end
I'm
of the
just saying that
project.
it wasn't available when I tried to search for it, that's all. I couldn't find it. That was-
Well, yeah, don't say it wasn't available, you can find it, that's two different conditions there. Your fuse, FU2, and I assume FU1,
Yeah.
could you tell me again why they are there?
Why there, if fuse 1 and 2 are there?
Well, fuse 2 is the one that you talked about, so
Yeah.
talk to me about fuse 2, why is it there?
So fuse 2 is other terminal that goes to the output terminal, connect through the fuse. So in case of overload or condition at the point of the motor, it will fuse up. Since I used a 5 amps fuse in this case, and
You use the 5 amps?
Yeah.
I thought on my schematic it says 1. It says 1 amp on my schematic, which I think is the same version as yours. 1.5?
no, it doesn't mention any.
Which version of your schematic?
This is the version 1.5.
Okay, well,
Fuse 2
clearly
is 1 amp.
says 1 amp on mine, and I
Yeah.
can't tell on that.
Did you print out the drawing package that was submitted the due date on the 20th, right? I mean,
This is the
this is
one.
the,
No, this is May 6th.
and they submitted May 19. Yeah, schematic was May 6th, that's right, yeah. But I'm talking about the Dropbox submission.
Well, I don't care, what I'm telling you is it says 1 amp here. I don't know what it says there.
That's not,
Five.
it looks like a 5, but it's
Can't
hard to
really-
tell. Look, could be a 3.
And I'm confused at the fact that you would have same version numbers,
Same day.
same day and everything, and you have different information. It comes back to, we had a previous, you guys aren't taking in the essence of version control and documentation control. Okay, so if we're doing this at a distance, or worse than that, I'm working on off of this document several years later, and I'm trying to fix, and it's supposed to be a 1 amp fuse. I put it in, it keeps popping fuses, I don't understand why. It says 1 amp, what's going on? And meanwhile, you have the updated version that says 5 amps, so how are you supposed to know? Because when I'm gonna call them and say, I've got revision number 1.5 here, and you're gonna say, well, I do too. Well, when we say that, that means it should be the same document.
Another thing I'm just noticing now is that there is no resistance or capacitor value on our copy. All there are is the reference designators shown.
That's right.
You have values on yours though.
Yeah, it's a restricted version of version 1.5.
Yeah.
I guess you'd say.
So anyways, I'll get back to the fuse, okay, assuming it's 5 amps, I guess. Okay, so what is the fuse there? What is it doing again?
So it's connected to the point, that's the AC connection, like AC side of the terminal.
Yeah.
And whenever the load at the motor's end or the load's end exceeds 5 amps on a certain surge, or however, if it exceeds that limit, it will cut off the connection to supply.
Okay, because I'm gonna quote, well, half quote, half paraphrase you. During your presentation, you said the fuse was there to prevent overload or over voltage conditions.
To the
Does
load.
the fuse protect against over voltage conditions?
Over voltage, the fuse for the over current condition, of course, over current conditions, but I haven't tested the over voltage, but the current I tested, it fused after.
Does a fuse protect for over voltage conditions in general?
Not from the over voltage.
Hmm?
It protects from, yeah, it protects from both over voltage or over current
A fuse has what for ratings?
currents.
current, and it does have a voltage rating, but the voltage rating is the maximum voltage you can put across the fuse so that when it goes open for current, it doesn't jump the gap.
Yeah,
In other
so
words,
it's
you-
basically
you-
protecting the overcurrent,
So a fuse is only there for,
overcurrent condition.
there you go, okay?
I'd just like you to re-explain, you had talked about the transformer, and I wrote down what you said. When you were talking about the transformer, you said, and this is a quote, the step-down part of the transformer. Can you explain to me what part of the transformer does the stepping down?
The
Or
secondary-
could you maybe re-explain that and use correct terminology?
Okay, so just to clarify that part, the input goes to the transformer directly, and this part of this primary winding, which is the 120, will find it, and this part is secondary winding, which will be the step down voltage at the output terminal of it, and that will be the step down voltage supplying to my rectifying bridge.
And what makes that a step-down transformer?
What the transformer characteristic, it's a signal transformer, and that steps down because of the windings in the secondary terminal, secondary side of the transformer, makes it step down the voltage.
And why does it step down instead of step up?
Because of the center tap, I believe.
I don't see a center tap.
Oh, I mean, because the transformer that I purchased, for the purpose, I needed a lower voltage, and by the data sheet of the transformer, that shows or that tells about the steps down of the voltage using the transformer from high 120 to low of 14.
So the data sheet is written because the transformer has a specific physical property.
Yeah.
So what physical property of the transformer causes it to be a step-down transformer?
Secondary winding.
Well, a step-up transformer has a secondary winding as well. So what about this transformer causes it to step down?
I haven't looked into that in the characteristics. How does it steps down? Since it says steps, like it does the step down the voltage from the.
You took at least 2 courses throughout the 2-year program here that talk about transformers and explain how that happens. So you must remember.
Plus, it's an essential part of your circuit.
It is, yes.
Google and stuff.
He doesn't have time to Google it.
No.
Okay, so the other question I had was, you had chosen a well, I can barely read it, but I think it says MOC 3021.
Yeah.
Okay. Why did you choose the MOC 3021 as compared to, say, an MOC 3031?
Okay, so when I started the simulation, and I was like, as I speak, for the zero crossing detection, I also used an LM324, but the breadboard, it wasn't giving me what I expected it to do. So similarly for the MOC 3031, the first one, as I mentioned, I tried to use the multisim. It has the MOC 3031. It's doing that part of the circuitry, but when I used the Proteus, I had various other MOC 3021 and 3031, and when I used MOC 3031, it wasn't giving me that triggering pulse to the track at that speed that I was expecting. It could be my LM324 problem, because I was using LM324 for the zero crossing detector. So I was just troubleshooting and making the changes to see what gives me better outputs with the oscilloscopes as in the test results simulation. This one giving me a better pulse, better wave of the signal MOC 3021. That's why I went for this one instead of MOC 3031.
When you use terms like better, like those are kind of subjective, like I need you to use more technical terms, engineering level terms that explain to me the reasons for that, because I don't know what better means.
Okay, so the output signals from the AC side of it, the optical couplers, the wave that was coming out of there was much choppier in this one rather than the MOC 3031. For my case, I need gradual increase of.
What do you mean by that?
Choppier.
Yeah.
Like, I'll show you.
You want to bring up the waveforms?
Yeah,
and
exactly.
Maybe this one.
Exactly. So this one is having enough cutoff or gradually increasing, but when I used MOC 3031, it was more fuller at the initial stage. So with the troubleshooting I ran with changing MOC 3031 and MOC 3021, this one satisfied.
Okay, so you were actually looking for a device that would give you portions of a waveform, not the full period? Is that what you're looking for? Is that what you're talking about?
No, I'm looking for a period, full wave of course, to run, to supply the motor, but the startup has to be the gradual and smoother. That's why I was trying to see which one is more compatible for the design. And that was part of the troubleshooting, to use various optical couplers.
Okay, so what do you call this? You have the MOC 3021
Yeah.
will generate, will output a portion of the, the sine wave, right? You're getting only a small portion in stage 2. In stage 1 it's absent. Stage 2 you're getting a small portion of the sine wave, and then you're adding more and more of this sine wave as you go, right? This is how this works, looks
Yeah.
like, right?
Yeah.
So what do you call that MOC 3021? The fact that it's not, that your waveform doesn't start right at the zero crossing. What do you call that action?
This part, stage 2.
Yeah, you could use that as an example.
Uh,
What type of device, what type of optocoupler generates that result, the one you were looking for?
what type of
Yeah,
optical?
what type of optocoupled device generates that type of waveform?
I think it's photodiode. It uses the technology of photodiode inside it, and the light inside the optical couplers does that pulse.
Okay, but that might also be true for a 3031, which didn't give you the same output. Okay, so what I'm trying to say is, or what I'm asking is what type of device gives this output here?
What type
There's a particular name for it, and you, when you said that the MOC 3031 didn't give you the result you were looking for, so you switched to the MOC 3021, it gave you this. What's this called?
What's that?
What's
called?
the MOC 3021, and how does it compare to the 3031? There are terminologies that go with each. What are they called?
As I cannot name it, since I'm not familiar, cannot recall the names, I would say. But the comparison I made with both components was with the help of oscilloscopes during the simulation process. And the simulation process, as I speak, MOC 3031 was giving me much fuller waveforms than the MOC 3021.
Yeah.
That's why I went
Well,
for
And
it.
there's a reason for that. Why?
What happens if you didn't have the models? Like, you got lucky, you picked one,
Yeah.
I'm not getting it, you picked another one, oh, I'm getting it. What happens if you don't have the models in your simulation?
I mean, when I reached the stage of breadboarding, and with the troubleshooting, I found out that my 0% detection IC is not working. I changed it to build up that circuitry. I would do the similar with that. If it's not giving me something that I was expecting, I would do more and more troubleshooting to find out what could be better to solve the
Is that the way troubleshooting?
So, I guess the root of my question, I'm trying to get you to understand the difference between a 3021 and a 3031. And there are two technical terms that explain the difference between the two. I was just wondering if you had come across that, and because you did note that the 3031 and the 3021 operate in two distinct ways, and I was just hoping to have a conversation and get you to kind of explain what the differences actually were. It sounds like you experienced that, but I'm just wondering if you could put that to words for us. That's all.
I would say I'm not familiar with the terminology about
Okay.
that.
So the 3021 is a random phase optocoupler, and the 3031 is a zero crossing, or a zero cross optocoupler, which is the reason why you, as you said, you got fuller sine waves from the, and that's the reason, right?
Yep.
Okay. Maybe it's that you already had a zero cross detector in your circuit, that you didn't, implementing a second one, what wouldn't be a good idea in this case. But I don't know if anybody else has a question, but I have a follow-up to this.
Well, I want to talk about the zero crossing, but go ahead.
Well, so do I, as a
Oh,
follow-up to that. So what is the problem with producing waveforms that look like this?
What is the problem?
Yeah, what's the problem? I don't know if that's.
No, that's a good one.
Okay,
Okay.
he says it's a good one, you gotta answer it.
I'll try. Problem with this ones and comparing with the fuller ones, you mean?
Well, I guess we could go that way. So the closer and closer you get, so stage 3 is almost a full
Almost the full
sine wave, right?
Sine wave.
So so the further and further away from a sine wave that you go, what's the issue?
So between these two, comparing between these two, as it's not,
Your battery died?
let's say,
Okay, well,
I think so. Can I bring the charger?
we know what the waveforms look like, just talk to us
Yeah.
about it.
I should have connected that.
That's okay?
Okay, so between the two waveforms, that one was less fuller than the other one. Stage 2 was less fuller than
Yeah.
the stage 3. So stage 2 has less voltage across the top and bottom of the waveforms, and that is what's giving the gradual increase of the voltage when it gets fuller or further.
Is it only less voltage that you're getting? Because I could actually take a 120 volt RMS sine wave, which has a peak value of what?
RMS.
What's the peak value?
120.
170, right?
170.
Okay, so I could actually take the 170 volt peak value and just reduce that down, right? But I would still have a sine wave, and I'd still get the same effect, right? You chose not to do it that way, which is fine, but I'm just wondering if you understand, you're not just reducing the sine wave amplitude, you're actually removing pieces of the sine wave, right?
Yeah.
From your full output compared to partial output,
Partial
right?
output, yeah.
So what's the disadvantage of doing it that way?
Disadvantage.
Yes.
It may not get the full wave
Yeah,
at the end of the.
well, we know it doesn't get the but what is the disadvantage of that?
Probably under voltage.
No,
The vol-
no,
full wave is the.
no, you want, that's what you want though.
But,
But what's the disadvantage in doing it that way?
in the stage 2? Or
Well, no, I mean
in a
just
hole.
your circuit,
In a
right? The way that your circuit handles this, right? The way that your circuit is modifying the waveform, okay? Such as to give varying voltage and varying power, right, to the load. What is the disadvantages, what is the primary disadvantage of doing it in that way, the way that you showed us?
The way I showed it.
Yeah.
Disadvantage. Disadvantage could be the delay, that would be much longer.
No. No, because I mean, you can make it delay whatever you want, okay? There is one disadvantage that your system has compared to if I just took a big variable resistor, right, and put it in series with that. There's other disadvantage of doing that. But what do you have when you have a sine wave? What do you have as a frequency?
as a frequency.
Yeah.
I can change 50.
Well, in North America, what is it? We're getting back into this European, North American thing again, okay? What is it?
Um, 100.
I scoped the waveform on the receptacle there. What am I gonna measure?
On the
Yeah, I put my scope on the receptacle and I measure that sine wave. What am I gonna get for frequency?
I guess 100 kilohertz.
100 kilohertz? Jeez, I don't think many things
No,
would
I
work
think
around
it is,
here.
adjusted, like when we're using the oscilloscope, changes the frequency to make it
No,
fit
no.
in the display, but
No, in North America, what's the line frequency?
cannot remember the top of my head.
Yeah, it's 60 hertz.
60 hertz.
Okay, so your device, when it's outputting that full voltage, like you say, it's 60 hertz, okay? So we go back to stage 2, okay, where it's gradually ramping up and you get this little sliver of the waveform. So that's 60 hertz sine wave, it's one pure frequency, 60 hertz, okay? What do we have when we go to stage 2 and we only got that little sliver?
It's half of that, or it's less than 60.
No?
Should be double. Like it should be either less than the 60 hertz that is.
It can't be less.
Can be less.
It can't be less. What's it gonna be? Will there still be 60 there?
No, it shouldn't be 60.
Yeah, there'll
because
be
the
60.
60 is the full wave.
There'll be 60. Because what you're doing is, and this is the disadvantage is you're adding harmonics. Okay, so the 60 hertz is still there, but you're adding harmonics over and above the 60 as well, which we don't have time to teach all that right now, but I thought that was something that you should have realized by doing a project like this. What's the problem with harmonics?
It's problem with the harmonics.
Yeah, you're introducing harmonics when you do that. What's the problem with that?
The problem with the harmonics probably would be the constant supply. If that doesn't match with the load, and the device may not.
Well, in a nutshell, harmonics can cause overheating
Overheating.
and various other issues with,
Overload, yeah.
yeah, and not just with this unit. What if the harmonics feed back into the electrical system in the college?
But
And these problems were happening all over the place.
that's why I had the two fuses. That was one of them was connected to the input source. So
That one.
Yeah, but a fuse isn't gonna stop that.
Harmonics, fuses aren't frequency.
They're not harmonic absorbers, right? So, anyway, we're out of time, I guess.
Yeah, we are.
Sorry, I took all your.
No, that was a great topic.
Okay. All right, thank you.
Thank you.
Yeah.